Welcome everybody. My name is Andrea Malchiodi and I'm the current director of the Giorgi Mathematical Research Center. So I would like to welcome you to the workshop Optimal Transportation and Applications, which apparently is arrived at its 10th editions. So congratulations to the organizers. I will just say a few words and promise I won't take much of your time. The Giorgi Center was founded about 20 years ago, formally as a research laboratory of Scuola Normale Superiore, but with the mission of being a center for the whole mathematical community in Pisa, so giving occasions for people to gather. And this community includes, apart from Scuola Normale Superiore, also the people from the University of Pisa and a smaller group from Scuola Superiore Sant'Anna. These institutions, especially the former, in fact, contribute financially and crucially to the activities of the center. So the main activities are, since the foundation, workshops, schools, and intensive research periods. We also recently started the colloquium series. So we have visiting positions of two types. There are 2 years postdoctoral positions, as well as visiting positions of short term to perform research in pairs. As many centers of this type were, of course, affected by the pandemic over the past 2 years and a half. We started last year with activities in presence with a short break during the past winter. So let's cross fingers for the coming year. So finally, I would like to thank the organizers for bringing up this very high quality event, and also the staff of the center for their constant and very valuable help. Thank you.
So welcome all to this 10th edition of the Optimal Transport Meeting. As you know, it was scheduled in 2020 and then it has been delayed several times. And so I'm particularly grateful to the speakers, but also to you all for having kept this commitment to come to Pisa over time. And indeed, we have restarted to live the joy of having meetings in presence. And also, given the local temperature, let's consider this as a summer-like meeting. So a special thank goes to the Centro De Giorgi, to its staff, led by Sabrina Bigazzi, to Giuseppe Savare, who among the us organizers had really a major role in arranging all the details of the meeting. So I think we can start. Let's enjoy the meeting, and I give the floor to the first chairman of this morning, Giuseppe Buttazzo.
Robert McCann from Toronto. And he will speak about pattern formation particle systems from spherical shells to regular simplices.
All right, so I'm very grateful to the organizers for giving us the chance to be here in Pisa. I'm going to talk about joint work that's with my student Cameron Davies, and my former postdoctoral fellow Tong-Suk Lim, who's now in the Krannert School of Business at Purdue University in Indiana. And I'm talking about pattern formation in particle systems. And my particle systems are going to depend on a pair of parameters, and in some range of, so this is a problem about self-assembly. In some parameter range, the particles are going to self-assemble into a spherical shell. In some other range, they're going to self-assemble into the, onto the vertices of a regular simplex. And there's a version of these slides not quite up to date on my website if you click on the talk button. Okay. So these kinds of models are used both in physics and in mathematical biology and also in some other areas. And I'm going to talk about models where you have a large number of organisms, and but they obey a simple force law. So if the organisms get too close together, they feel uncomfortable, they repel each other. If they get too far apart, they feel lonely and they come together. And this is the kind of model that's used sometimes to explain flocking in birds and milling patterns in school of fish. I'm going to look at a sort of simplified and stylized version of these models. That's from a different view. And there's lots of models like this. And today I'm actually going to be talking about power law potentials. So I guess going back almost 100 years to explain chemical bonding, the Leonard Jones proposed a power law potential in which the repulsion has power. I guess the repulsion has power 12 and the attraction has power 6, so-called the 612 potential. And going back about 50 years or 70 years, these kinds of models started to be used in mathematical biology as well in the work of Reader. And there's famous work by Keller-Siegel that probably some of you have worked on yourselves, where you have it's a model for chemotaxis. I guess in 2 dimensions, it's a logarithmic attractive potential, so it's purely attractive. And molecules lay down chemical markers, and these markers are used, not molecules, organisms lay down chemical markers, and other organisms of the same species use these chemical markers to follow to cluster to food sources. And actually in the Keller-Siegel model, in some situations, all of the organisms are going to collapse on a point, and you can try to investigate the asymptotics of that collapse. And if you blow things up, so they're collapsing at a certain rate, and if you zoom in at that same rate, what you'll see is that the particles are actually converging in this parameter regime to a spherical shell, in some other parameter regime to the corners of the simplex. When I give this talk in Canada, I highlight the Canadian contributions in red, but since this is an international talk, you can disregard the coloration. So dynamical models go back about 20-25 years. There are these 1D models by Alex McGillner and Leah Edelstein-Cachette, where you have this competition between the attractive repulsive interactions that I've been describing in diffusion. There are different kind of dynamical models. This is a first-order dynamical model. There are also second-order dynamical models where it's the acceleration rather than the velocity, so where you have inertial effects due to Levine, Rappel, and Cohen, and also Kruger and Smale. And in the last 10 years, there's been just a great proliferation of analysis, and I wrote down some of the names of people that have worked on these models, but I'm sure that I missed people as well, so I apologize if you're not on my slide. Right, so for simplicity, I'm going to look at differences of power laws. I'm going to have an attractive power A and a repulsive power B. I'm afraid that in the paper it's alpha and beta, but in my slides it's A and B. And I'm going to normalize these attractive repulsive potentials so that the minimum of the potential energy well occurs when the organisms are 1 unit of distance apart. And that's just a choice of units. Of course, the physical range of parameters are the ones where probably both A and B are negative. And so the strength of the repulsion increases at the origin, and it decreases at large distances. But I'm going to talk about a different parameter regime today. I'm going to talk about the opposite parameter regime. So this is the physical range down here, both parameters negative. I'm going to talk about both parameters positive. And so the profile of the interaction, it will still be minimized at 1. It will be repulsive, but flattening out at the origin, so not so strongly repulsive. And this is going to permit all of the organisms to accumulate on a single point. Like, they don't want to do that, but it doesn't cost infinite energy to do that. It only costs a finite amount of energy. And my interaction is going to grow at large distances. So this might not be so physical, this sort of infinite forces, growing forces at large distances. On the other hand, and I'm going to mostly be talking about an energetic formulation of this problem. So I'm going to be talking about global energy minimizers today, but one can also think about local energy minimizers in an appropriate sense. And in terms of local energy minimizers, the particles are only going to care what the potentials are doing locally. And so the conclusion will be that the equilibria that I described today, although they're going to be global energy minimizers for this not so physical potential, there's still going to be local energy minimizers for other potentials that have the same behavior as the not so physical potentials, at least in the range of interactions that you see. So if all the particles are distance 1 from each other or distance 0 from each other, and your potential agrees with this one, your distance 1 and distance 0, then the configurations I described today will still be local energy minimizers for your potential. Great. So as I say, I'm going to talk about what's sometimes called the mildly repulsive regime, because the interaction is not so strong at the origin. And it's the parameter range where both A and B are bigger than 2. And you also need A to be bigger than B because you want this difference to have a local minimum and not a local maximum at unit distance. There's another parameter regime which is mathematically tractable, which is when A is between 2 and 4 and B is negative. And Orlando Lopez showed a few years ago that the interaction energy I'm going to describe is actually convex in this region. And so in this green region, you know, the energy minimizers for this interaction are going to be rotationally spherically symmetric. But that won't necessarily be the case in this red region that I'm going to talk about. Okay. So if we think about particle dynamics, you can give a description in terms of ordinary differential equations or in terms of partial differential equations. So if I had finitely many particles, say J particles, and the interaction between them is given by the gradient of the power law difference that we saw on the previous page, you can just imagine summing up the interactions between the kth particle and all the other particles, and this would give the force law here. If you normalize by the number of other particles, then you can also take a kind of limit as the number of particles goes to infinity. But in order to take that limit, it's useful to reformulate this dynamics as a partial differential equation for a probability measure mu, which is basically the particle density. So I sum the Dirac measures at all the particle locations, I divide by a normalization constant, and then the dynamics of this measure mu will be what's sometimes called the aggregation or the self-assembly equation. It may be familiar to a number of people in the audience, but it says that the rate of change of mu is given by a conservation law, where the flux of particles is given by mu times the gradient of the interaction, and the interaction is our potential convolved with mu. So it's a quadratic equation in mu, nonlinear. And if you think of this convolution as being it's the variational derivative of the following energy. So this energy is going to be a Lyapunov function for the dynamics, and it's also going to be this is a Wasserstein 2 gradient flow for this energy in an appropriate energy landscape. So when I use the quadratic distance from optimal transportation to metrize the distance between two probability measures, then this dynamics is telling me to decrease this energy as quickly as possible relative to the distance between the adjacent states, mu at t and mu at t plus epsilon or t plus h. Questions? So actually, most of the talk is going to be devoted not to the dynamics, but rather to the statics of this problem. And so I'm mostly going to be focused on the question of for which probability measure is this quadratic energy that depends on these two exponents, a and b, assuming it's minimum. And of course, the problem is translation invariant. So if I translate mu around in Euclidean space, I don't change the energy. And so the best I can do is to find the minimum energy state up to translations. And of course, the problem is also for these energies that I'm looking at where the interaction depends only on this distance between particles, it's also going to be rotationally invariant. And so that's another symmetry of the system. But let me show you some pictures. For some parameter values, the energy minimizer, the global energy minimizer, will reflect this rotation invariance, and for other parameter values it won't. So that's somehow where the pattern formation comes into the discussion. Right. So it's a Wasserstein 2 steepest descent on the space of probability measures. I'm just fixing a little bit of notation on this slide. This is the limiting dynamics as the number of particles goes to infinity. And I guess if I have a subscript C and a superscript 0, because the problem is translation invariant, it's useful to consider the set of densities which have center of mass at the origin and finite, let's say compactly supported or finite second moments, whatever you like. And of course, you can expect that these global energy minima, it's natural to expect that these global energy minima are going to be attracting fixed points of this gradient flow. You can also expect that for local minimizers in a suitably strong topology. But it turns out that this expectation is a little bit frustrated. It's not quite true. Or you have to be very delicate. Yes, they're fixed points, but whether they're attracting or not is a delicate question. And it turns out that in lots of cases of interest, they're not actually attracting. They're non-repelling, but they're not attracting. So here are some numerics. These are numerics of Ted Kolokolnikov and his collaborators from 2013. And this is actually numerics not for differences of power laws, but for piecewise linear force laws. so piecewise quadratic potentials. And there are two, after normalization, there are two parameters defining the two quadratic pieces of the potential, also called A and B. And the point of this slide, and what we're looking at are the long time steady states of simulations starting from various initial conditions. And so what we see is that for some choices of parameters A and B, you get spherically symmetric steady states, but still with structure on different scales. For other choices of the parameters B, you might get, for example, all the particles coalesce to the corners of an equilateral triangle, and then maybe the triangle rotates around. And this is a simulation by Albi, Balaguer, Carrillo, and von Brecht from about the same time. This time it really is power law potentials, and it's in this, what we call the mildly repulsive regime, where both parameters are larger than 2. I think that the attractive parameter is fixed to be 2.5 in these simulations, if I remember correctly. Oh no, it's fixed to be 5 in these simulations. And we're looking at 3 different values of the repulsive parameter, a value of 1/2, a value 1.5, and a value 3.5. And so when you read time on the horizontal axis here. So the initial condition is at the left side. After a few thousand steps, 2,000 steps is on the right-hand side. So you start out with this initial condition and this fairly strong, moderately strong repulsion, and the particles push away from this circle, and then they eventually sort of coalesce into this wave, which is concentrated near the circle but not on the circle. If you decrease the repulsion a little bit, so it's not quite as strong, then you don't get this wave anymore. After a while, what you get is everything on the circle. And if you make the repulsion really weak, like the mildly repulsive regime that I'm going to mostly talk about, you get symmetry broken and the particles all coalesce into the 3 corners of an equilateral triangle. And so basically the purpose of the work that I'm going to describe is to try to explain the patterns that we see. Yes, there's a question? Yes. This is a dynamical simulation, yeah. Other questions? Right, so here's my parameter regime once more. And the point is that the stronger the repulsion is, so the lower down you are in this picture, the more difficult it is for the particles to congregate close together. So if the repulsion is actually negative, if you're down here, the particles are probably going to be smeared out. And there's a quantitative statement of this that goes back to work of Balaguer and Carrillo and collaborators, which says that as soon as the repulsion parameter B is less than 2, then you get a bound on the Hausdorff dimension of the support. So the Hausdorff dimension of the support is at least 2 minus B when B is less than 2. And so you can't, so below B equals 2, you can't have all the particles collapsing onto countably many points. But I'm going to mostly talk about B above 2 or equal to 2. Right. And actually, so when we talk about local minimizers for these problems, it turns out that the choice of topology is very delicate. And already in my PhD thesis 25 years ago, when I was thinking about rotating stars, I was confronted with this problem. So the story about rotating stars is that if you have, if you have particles of gas that are interacting with other particles through, say, Newtonian gravity, so that's attractive, it's wanting to make everything collapse to a point. On the other hand, probably if you're really modeling a star as a fluid or a gas, then when you squeeze a fluid hard, it pushes back. So there's some pressure and the first question is, can the attraction due to gravity and the repulsion due to pressure balance each other? And under appropriate assumptions, yes. If gravity is too strong, no, it will collapse. If the repulsion is too strong, no, it will diffuse out to infinity. But in an intermediate range, yes. And then if the star gas is also rotating, so it has a certain amount of angular momentum, you can try to minimize the total sum of these 3 energies: the gravitational potential energy, the energy of the internal energy of squeezing the pressure, and the total kinetic energy of the rotation, subject to a constraint on the total amount of mass and putting the center of mass at the origin, and fixing the total angular momentum around the center of mass. And it turns out that for non-zero angular momentum constraint, there's no global energy minimizer. And more or less what the gas wants to do is it wants to depending on whether the angular momentum is large or small relative to the amount of gas, it wants to coalesce into either a single rotating body or maybe a pair, like say a binary system, with two masses orbiting each other. And it's, in fact, when you have two masses orbiting each other, you could always win energy by evaporating mass from the smaller component and putting it down on the larger component. And the problem, and that's in any kind of vector space topology on the density, that's going to be evaporating mass here and growing it there is going to be a continuous operation. So in any kind of vector space topology on the densities, you can't have local minima, nor can you have local minima in, say, the W2 distance, the Wasserstein 2 distance. But it turns out you can have local minima in the Wasserstein infinity distance. So the idea is that there's a potential energy barrier that to evaporate the mass here and put it down there, you need to carry it from here to there, and it crosses through a potential energy barrier. And the Wasserstein infinity transportation distance makes this a discontinuous operation. So in that sense, you can have d-infinity local minima. And about 10 years ago, Balaguet and collaborators showed that in this purely interactive model that I've just described to you, you also can have these d-infinity local minimizers. And moreover, the Hausdorff dimension of the support is bounded below by 2 minus b, if b is larger than 2. At about the same time, Sun, Uminsky, and Bertozzi were investigating the collapse in the Keller-Siegel model, the self-similar collapse, and they were asking, is it spherically symmetric or not? And what they showed using a linear stability analysis was that if the repulsive parameter is exactly equal to 2, which is the correct parameter for rescaling the dynamics at the rate of collapse, then whether or not you get spherical shells depends on whether A, the attractive parameter is larger than 4 or less than 4. And they showed linear stability of the spherical shell when A was less than 4, and they showed instability when A was bigger than 4, and when A was bigger than 4, they showed that actually putting all the particles on the vertices of a regular equilateral triangle was linearly stable. And then two of the questions that they left open was, is this linear stability actually predicting nonlinear stability, and whether the patterns that they described are globally stable, globally attractive or not? So I'm going to give some partial answers to those questions today. And about 5 years ago, Carrillo, Figali, and Patacchini showed that in this mildly repulsive regime, when B is strictly larger than 2, then any d-infinity local minimizers for this problem are going to be supported at isolated points, and if they're global energy minimizers, at finitely many points. And so we'll be refining this to show that, in fact, they're supported at n+1 points, namely the vertices of a regular simplex. I guess we're not showing that I'm not going to show that all d-infinity local energy minimizers are supported on the vertices of a regular simplex, but I'm going to show that every distribution of mass over the vertices of the regular simplex is a d-infinity local energy minimizer. And in one dimension, my collaborator Lim with a Korean team of collaborators showed that they were able to catalog the d-infinity local and global energy minimizers for a certain range of parameters. Great. So what are the results I'm going to talk about today? First of all, in this, when B equals 2, which is the rescaled self-similar Keller-Siegel collapse, in the interval A between 2 and 4, we're able to show that indeed a thin spherical shell is the global energy minimizer unique up to translations. And so that allows us to show that the linear stability found by Bertozzi, Sun, and Uminsky is in fact non-linearly stable. It's not global. It turns out not to be a global attractor. It turns out not to be a attractor at all, in fact, because so for example, in 2 dimensions, you have a circle of mass. That's the global energy minimum. It can be approximated by a discrete ring of masses. And the more points you have in the discrete ring, the closer you are to the circle in any topology, including the d-infinity topology. But so you have sort of these nearby stationary points as close as you like. So your circle is not attracting anything, but on the other hand, it turns out to be Lyapunov stable. So if you start close enough to the circle, then you never wander too far away from it. And our other major result is going to be that, so we have this comparison result that says, we can classify all the minimizers exactly at the point 4,2. And we also say that And one of the minimizers here includes the distribution where you put all the particles, you scatter all the particles uniformly over the vertices of a regular simplex of diameter 1. And whenever that thing is an energy minimizer, if you vary the parameters to make both A and or B larger, that thing will still be an energy minimizer, and in fact, it will be the unique minimizer. So everything that lies above or to the right of this point, or both, will be uniquely minimized by concentrating all of the mass on the corners of a unit simplex. So this is one of the cases where you get rotation broken. There's a whole family of minimizers, but it's unique up to translations and rotations. And I call this threshold B equals 2 the centrifugal line, because in 2 dimensions, this B equals 2 exactly corresponds to the repulsion is the same thing that you would see if you put all the particles on the turntable and spun it with constant angular velocity. So that tends to make the mass push away from the center, like a centrifuge. Okay, so here's our theorem. I'm going to state it for dimensions at least 2. We have versions of it for dimension 1, but they're slightly different. The statements change a little bit in dimension 1. So again, if we're on this red line where A is between 2 and 4, and if B is exactly equal to 2, the energy is uniquely minimized by uniformly distributing the mass over a sphere of an appropriate radius. If A is 4 and B is 2, then a configuration mu minimizes the energy if and only if the support of mu lies on the sphere of this radius. And if the second moment of inertia tensor of mu agrees with that of the thin sphere described in point 1. So if it's this radius squared times the identity matrix divided by the dimension. So there are lots and lots at this point here where the blue region met the red line, there are lots and lots of minimizers. You could put all the mass uniformly on the corners of a cube. You could put them in 3 dimensions uniformly on the corners of an octahedron, a dodecahedron, a icosahedron, all the platonic solids. You could take convex combinations of these things. Lots and lots of minimizers. So actually, at this point, the dimension of the set of minimizers becomes infinite dimensional. On either side of it, you have a finite dimensional set of minimizers, given where the dimensions, the number of symmetries. And so then we sort of investigated the threshold between the region where these corners of an equilateral regular simplex and the spherical shell is, and we find so there's some threshold A that depends on both dimension and B, such that if you're above, so if A is larger than this threshold, I don't like this statement so much. Yeah, so if A is bigger than or equal to this threshold, then these guys are minimizers, and if A is strictly larger than this threshold, these minimizers are unique up to rotations and translations. So this is what I call sometimes the balanced simplex. You could also think about cases where the coefficients in front of these delta measures are not all equal to each other. Those are the unbalanced simplices. Those are still local, d-infinity local energy minimizers. They're not global energy minimizers anymore. But if you think about the dynamical simulations we were looking at the beginning, whether you converge to the global energy minimizer or one of these local energy minimizers with slightly different masses on the corners of the simplex is going to depend on which initial conditions you started with. So even the local energy minimizers turn out to have some kind of local stability in this d-infinity metric topology. And finally, we're able to estimate, so maybe I should go back 2 slides. So basically what I'm telling you is there's some transition curve in this white region that separates a blue region where the minimizers are all concentrated on the corners of a regular simplex from some white region where those guys are no longer global minimizers. And we don't actually know what the global minimizers are until we get down to this line where we know they're spherical shells again. And so I'm going to try to, what can I say about this curve separating the blue region from the white region? Well, I can't specify it exactly, but I can give upper and lower bounds for it. And it turns out that in 2 or more dimensions, the upper bound is independent of dimension. The lower bound depends on dimension, but the lower bound converges to the upper bound as the dimension goes to infinity. So these are asymptotically sharp in large dimensions, the bounds I'm going to give. And The bound is given by solving this equation, Fn of A equals Fn of B. So of course, A equals B is one solution, but there'll be a second solution, A larger than B, of this equation. And where these F's are given by these two functions here. And you can see that as n goes to infinity, the Fn converges to the F infinity, which tells you that this lower bound converges to this upper bound. And moreover, this function is unimodal. So it grows for a while, it has a unique maximum, and then it comes down. And so for any given B, there will be only two values of A for which this equality can be satisfied, namely B itself and some other value. And so it's that other value that defines this threshold. And maybe I'll have time to say a little bit about where do these bounds come from, something about where they come from. So overall, the picture, replacing A by alpha and B by beta, this is the picture we get overall. We have this is, I think, in two dimensions. We have the red upper bound, the black lower bound. Somewhere between them is a continuous monotone curve, which separates the region where the particles are minimized by uniform equidistribution over the corners of a regular unit simplex from the region where they aren't. And the other thing, we know a little bit more about these curves. We know these curves hit the diagonal at 90 degrees. And there's nothing above the diagonal, because above the diagonal would correspond to choices where the potential doesn't have a global minimum, it has a global maximum instead. But that turns out to be an issue of normalization, as we'll see. And we're able to characterize this transition threshold in another way as well. So this function a(n) of b, the true function, the one we don't exactly know, we know that when a is exactly this threshold, one of two things happens. So here, my script p with the subscript delta is the set of measures which are equidistributed over the unit simplex. So when a is larger than b, this is exactly the set of minimizers. And when a equals b, we say suddenly it's a strict subset of minimizers. So there are other minimizers as well. Or else, the support of nu, which at a minimizer has to be a subset of the set of points where the potential convolved with mu attains its own minimum, becomes a strict subset. So one of these two inequalities has to break at the transition threshold. And if the first one breaks, what it's telling us is that, yes, there are other minimizers, but they're far away. And so that means the bifurcation from my equidistribution over the unit simplex to my other minimizer when I lower a through this threshold is discontinuous. I can't suddenly deform the amounts of mass by epsilon or move the points around by epsilon. It suddenly has to jump to a really different minimizer. Okay, so now let me spend the time remaining talking a little bit about the ideas of the proof. So of course, in the case where a is less than 4, this convexity that was observed by Lopez is the main tool that we use. And it says that the interactions through this attractive energy lead to a strictly convex functional. At least on the space of centered, this would not be true if I didn't center the measures with their center of mass at the origin. And the measures have to be neutral. So I have to be looking at the distance between two probability measures, not two measures with unequal masses. And basically, he shows this by Fourier transform. So this is my energy, my purely attractive energy. I can also write it in terms of the Fourier transforms rho of mu in itself. And then it's basically, it has a sign, and the sign is given by this overall coefficient. The coefficient involves gamma functions, but for this parameterization, for this range of parameters, it's a positive coefficient. And so that says that if I was trying to minimize this purely attractive energy in this range of parameters, the minimizer would be unique and spherically symmetric. And its Euler-Lagrange equation is basically that all of the mass of mu has to concentrate on the minima of the variational derivative, which is v convolved with mu. And but we need to know one more thing. We need to know to show that. So this sort of tells us the minimizer is spherically symmetric, but not that it's concentrated on a single sphere. Maybe it could be a union of spheres of several radiuses, like we saw in the simulation. And so in order to prevent that, we need some kind of analytical inequality. And it turns out that if we look at the variational derivative of the energy again, so v convolved with mu at a2 as a function of the radius, the third radial derivative of this turns out to have a sign, which means that this function, it's positive. So this function can start out concave and then become convex, but it can never be concave again. Or if it starts out convex, it can never become concave, because for that to happen, this third derivative would be too negative. And if you compute this third derivative, it's actually quite a complicated expression. It's an integral over a spherical shell. Or if it was some other radial thing, it would be a sum of terms like this, of spherical shells of different radiuses. But the point is that this integral has a sign. And for a equals 4, this was anticipated by Hanji Dan, and for smaller values of a, we show it. Sorry, maybe I should leave the integral up for a second. So now I'm going to move to the case a equals 4 and b equals 2. I didn't say much about what b equals 2 is doing. I should have done. If a is 2 in this integral, it turns out that this a priori convex function of mu is affine linear. And so b equals 2 doesn't contribute to the convexity of the overall energy if I look at EA2 at all. So somehow the considerations that I was describing for the purely attractive energy also apply to the attractive repulsive energy, provided the repulsion is biparameter 2. So I guess I discussed that a little bit here. So it turns out that E2 is affine linear on the space of centered probability measures with compact support. And it's strictly convex, and E4, which we know is convex, is going to be strictly convex unless the moments of inertia of the two distributions agree. And so when you add something linear to something convex, certainly there will be a spherically symmetric minimizer, and other minimizers will have to have the same energy, which means the strict convexity will have to fail for other minimizers, which means they'll have to have the same moments of inertia tensor as the spherically symmetric guy. So in other words, this matrix of inertia the moments of inertia will have to be a multiple of the identity matrix, the appropriate multiple of the identity matrix. And that leads to our characterization of solutions in the case a equals 4, b equals 2. And more or less, you can see this from some chain of inequalities. So any other minimizer has to have its moment of inertia tensor has to be a multiple of the identity matrix. It has to agree with the spherical shell. And among such mu's, whose moments of inertia tensor are multiples of the identity matrix, Jensen's inequality tells you that you'll have a strict inequality, strictly larger energy, unless all of the mass is concentrated on this shell of radius, this guy, corresponding to this constant. Okay, and so now I move into the regime where a is larger than 4, or b is larger than 2. And so we have this comparison principle, and which I already described in words, but it says that if you have some a and b where the uniform equidistribution over the corners of the unit simplex minimized, then for all larger a and or larger b, that distribution is going to be a unique minimizer up to rotations. And so basically it's convenient to renormalize this potential by dividing by the geometric mean of a and b. Not the geometric mean, the harmonic mean of a and b. And when you do this, you make the picture in the parameter space a and b, you make the picture symmetric across the diagonal. And that's the thing that tells me that these transition curves are going to hit the diagonal at 90 degrees. And it turns out that this renormalized guy is monotone with respect to variations of the parameter b, or by symmetry, the parameter a. And so what that means is, coming back to our picture, if okay, so what I somehow want to picture is the energy curve, the potential, which was repulsive at small distances and then had a unique minimum and then grew. What this monotonicity means, so this monotonicity collapses when r is equal to 0 or 1. So the potential doesn't increase when r equals 0 or 1. It increases if r is anything else. And so, of course, the particles that are concentrated on the corners of the unit simplex, they only see other particles at distance 0 or distance 1. And so their energy doesn't change. Any other distribution, the energy will increase. And so if my equidistribution over the unit simplex is optimal at some a and b, and I then increase either a or b, it stays optimal, but other guys increase their relative energy with respect to it. So that's somehow what leads to this picture, where I know that if I have a point on this curve, everything above and to the right of that point is also going to have the same set of minimizers. That's what tells me the monotonicity of this curve, and with a little more work, it tells me the continuity of this curve as well. And again, the symmetry under reflection around the diagonal tells me this curve has to hit the diagonal at 90 degrees. Okay, so now I'm gonna, I don't have so many minutes left because we started a little bit early, but I'm gonna talk a little bit about local energy minima rather than global energy minima. And so with LIM, I have an earlier result which appeared. So by the way, the results I've been talking about today are supposed to appear soon in SciAm Journal of Applied Math and Communications in Mathematical Physics. A couple of years ago, we have a paper in Archive for Rational Mechanics and Analysis where we also studied this regime. It's less quantitative, but we study this regime A larger than B larger than 2, and we show for any set of masses, which sum to 1, this sum of Dirac measures concentrated on the corners of a unit simplex will be a local energy minimizer, and strictly minimizing up to rigid motions. And that's the thing that tells me that the bifurcation of the global energy minimizer has to be discontinuous, because I can't, even when I hit the transition curve, I can't find other configurations close to my equidistribution which have the same energy as it. So what is the d-infinity metric? Hopefully some of you know, but if not, here I define it. So here's the Wasserstein metric of order p. You get it by minimizing the expected pth power of the distance over all couplings gamma of my two given measures mu and nu. Now, for any finite value of p larger than 1, this metrizes the weak star topology, or the weak topology, or weak star topology on the probability measures with compact support and given marginals mu and nu. D-infinity is defined as the p-infinity limit of this thing, but D-infinity does not metrize the weak star topology anymore. It metrizes a much finer topology in which tunneling becomes a discontinuous operation. So in other words, 1 minus tx naught plus tx1 is a completely discontinuous curve as a function of t. And this is exactly the topology that prevents you evaporating mass on the lighter component of the two binaries and putting it down on the heavier one, or evaporating mass from one of the corners of the unit simplex and putting it down on a different corner. So they're both local energy minima, but to get from one to the other, you need to strictly increase the energy. So a student of, I think, Diogo Gomes and Dejan Slepčev in 2014, Roberto Simeoni, showed that at least in the plane, these d-infinity local energy minimizers and other discrete ring type solutions actually enjoy some nonlinear stability properties. But as I mentioned, the existence of discrete rings of large numbers of masses approximating the continuous shell, which are stationary for the dynamics, so they're critical points of the energy, shows that the spherical shell, even when it's a global minimum, can't attract nearby. So there's no neighborhood, even there's no matter how small you take the d-infinity neighborhood around the spherical shell, there will be discrete ring solutions which are other stationary points and therefore don't converge towards it. So you can't have asymptotic stability. So in what sense can you have stability of these configurations? Well, you can have sort of Lyapunov stability. So whenever I have a coercive function on a metric space, meaning it has compact sublevel sets, then for every pair of parameters, epsilon and delta, I can, if I choose H larger than the minimum, then I'll be able to take a delta neighborhood around the set of minimizers that's contained in a sublevel set. But the sublevel set in turn is going to be contained in this. I think I've normalized this to the minimums at 0. So it's going to be contained in a slightly larger neighborhood of the minimizers. And so the idea is that if I start with energy less than this H, I have to stay in this neighborhood of the minimizers. And for any epsilon, I can find such a delta, such that if I start very close to a minimizer, I stay in an epsilon neighborhood of the minimizers. So that's the Lyapunov stability. And it turns out that that's exactly the kind of stability we have around these energy minimizing configurations that I've described. So in other words, we can show that the energy that we're interested in satisfies the hypotheses of this theorem, and therefore that we have this with the d-infinity metric. So I think that's the statement here. The dA metric even. So you take, which transportation metric should you take? You should take the exponent equal to the attraction parameter, which is the larger of the two parameters. A is bigger than B. And then Lyapunov stability holds by basically 2 applications of Jensen's inequality. And so what that tells me is if I start for any epsilon, I can find a delta neighborhood of the minimizers. So if I start with energy close enough to minimum, the dynamics that I described decrease this energy, and so I will stay in that level set, and so I will never go further than epsilon from the family of minimizers, which in our case are maybe the set of all uniform distributions over the unit simplex and their rotations and translations. Okay, so I think I've said most of what I wanted to say this morning. Thank you very much for your attention.
Thank you, Robert. Is there any question?
Hi. Do you know whether there could be possibly Loeschewitz type inequality?
Loeschewitz. I guess we haven't really thought about it, but wouldn't if you had a Loeschewitz inequality, wouldn't that imply asymptotic stability?
Well, there are different kinds. So there is a variant. So maybe, okay, I mean, maybe the most classical one. There are also inequalities in which you bound from below the norm of the gradient in terms, say, of a power of the distance from the critical set.
Right.
And so it doesn't tell you where you converge, but it might tell you that you converge somewhere. So it avoids maybe an oscillatory behavior between different critical points.
Right. Okay, so I have not thought about this, but it can handle critical points at different energies. So it can handle a sequence of critical points whose energy converges to the minimum.
Yeah. So the classical one is bound in terms of somehow the height from the minimum, but there is also a variant in terms of the distance from the critical set. So that might.
Yeah, that would be interesting.
Thanks.
Other questions? So I have a question about the general. If you have a general potential of V of x,
yes,
are there conditions which guarantee that the solution mu is compactly supported?
Well, so I would look at the Euler-Lagrange equation, which says that the support of mu has to live on the set of minimizers of mu convolved with my general potential. And so I guess if the potential is growing in infinity, then that would preclude. I'm not sure. I haven't thought about it seriously. I think Guy also had a question. Maybe.
Oh, Guy.
In the same spirit as a question by Giuseppe, you mentioned the case where you have only the repulsive part of the energy, but I think you substitute you consider constraint on the second order moment of mu, which plays a role of confining potential in some sense.
Yes. And
so, in general, does it exist an external potential which makes the same job as attractive part of the initial energy? That means EB, according to your notation.
Yeah. I mean, so I think B equals 2 is trying to do something like this, but it sounds like you're wanting to substitute a 2-body potential with a 1-body potential. So it's not quite the same thing, but it's closely related.
Okay. Because in many situations, the global minimizer can go to infinity. There is a loss of mass at infinity.
Right.
Which is not the case here because you have the EB part.
That's right. There's also another. You can also look at problems where you take a compact where the particles live on a compact manifold, and then. So you can sort of throw away the attractive part of the potential and replace it by compactness of the manifold, and then look at purely repulsive problems. And so I was telling Professor Sturm about this on the way over here. So there's this nice conjecture by Fayes-Toth, which has to do with particles that live on the projective sphere. And Fayes-Toth conjectured 50 years ago or 70 years ago, it's still an open problem. If you have a collection of, say, a finite number of particles on the projective unit sphere, and they repel each other with a force independent of distance. You would like to understand the equilibria, and the conjecture is that you'll find some orthonormal frame where all of the particles live on the vectors of the orthonormal frame, and they're as equidistributed as possible. So, in other words, for the two-dimensional projective sphere in 3 dimensions, if the finite number is a multiple of 3, you'll have an equal number of particles on each of the basis vectors, and if it's not a multiple of 3, you'll have an almost equal number, +1 here and +1 there. Yeah, and that problem has an analog where we, instead of looking at repulsion independent of distance, you look at repulsion proportional to some power of the distance. And it turns out, again, there's some threshold in the powers. We don't know exactly what the threshold is, but we know that it's strictly between 0 and 1. No, we know that it's less than 1. And where for any larger, stronger repulsion than that threshold, the conjecture would be true. The conjectured minimizers would be indeed the global minimizers, unique up to rotations. And what we don't know is whether that threshold, which we know is strictly less than 1, is actually equal to 0 or not. So that's the open part of the conjecture.
Thank you.
Any other question? If not, thanks to Robert again.
And let me also thank the member of the audience that provided the laser pointer. Thank you.
So the second speaker did not show up. So he's in Pisa. He arrived safely in Pisa, but we don't see him. So I propose to switch, and now we have Pierre Cardaliaguet. Okay, Pierre Cardaliaguet from Paris-Dauphine. He will speak about weak solutions for mean field games with a common noise.
Okay, thanks. Thank you very much for the introduction, and thanks to the organizer for the invitation. It's really a great pleasure to be in Pisa again after some time. So I will discuss about the joint work with Takis Ouganidis from Chicago, and it's about mean field game problems. Does it work? Here it's better? Okay. So it's about mean field games problems. So as in Robert's talk, it's about limits of particle systems. But in contrast with Robert's talks, the particle system, the particles are rational in the sense that they are trying to minimize some cost. Okay, and this gives you a system which is slightly more complicated than just a transport equation. So let me show you the equation, which are a little bit ugly, but which are standard in mean field games problems. So they take the form of, okay, so for this one, so they take the form either of a system of stochastic partial differential equations or scalar partial differential equation, deterministic, in the space of measure. So let me go slowly about these equations. So the first one is a system of stochastic partial differential equations involving 3 unknowns, U bar, V bar, and M bar. So the one which is more familiar to you is certainly the second one, which is a kind of Mach inverse of equation involving a measure which evolves in time, M bar, okay, and which evolves in time randomly because of the Brownian motion which is here. Okay, so this equation describes the evolution of the particles, and these particles are submitted to a noise, which is here called the common noise, which is a Brownian motion. Okay, and each particle is made of an agent. So in economy, it's a consumer or a firm, okay, trying to optimize some cost, and therefore there is some Hamilton-Jacobi equation floating around, which is precisely the first equation. So the first equation describes the value function associated with one particle, and it turns out that this is a backward Hamilton-Jacobi equation involving a Hamiltonian like that, okay? And again, the common noise pops up through this W. Okay, and the V here, which is a function of time and space, is here in order to ensure that the value function is adapted to the filtration generated by the common noise. Okay, so you have this coupling between Hamilton-Jacobi equation and Fokker-Planck equation, okay, and through the common noise. And what we are interested in is finding a solution to this equation, of course, okay? And sorry, I forgot to describe the F. So indeed, there is this Hamiltonian term, which is typically a half of the U square, okay, which is really standard in this business. And the F is precisely the term which couples all the equations together, the two equations together. Okay, so it's a term of interaction between the players. So in economy, it's typically a price, okay, which couples all the consumers, or for the firms or something like that. Okay, so it's a non-local function of the measure M. So it's a function of the position X of the guy and of the measure. Okay, so if you make a huge effort of imagination, you take. Yeah, go ahead. No. It's usually it's not. Well, it depends, but in many cases it's non-linear. It's typically a variance or something like that. Okay. So if you make a huge effort, so you assume that beta equals 0, that there is no F, no coupling between the equation. Okay, so you try to do that. Okay. Then what you find is a usual system of necessary condition for the W2 the Wasserstein distance. Okay, so coupling the Hamilton-Jacobi equation with the transport equation, the continuity equation. Okay, so it's kind of generalization. Here there is noise. So one thing, there is noise, and second thing, there is just an initial condition for the measure. So I'm here in infinite time horizon. Okay, so there is. So we are living on 0 plus infinity. Okay, so there is no terminal condition for the measure. Okay, so that's the main difference. Okay, so people in economy don't like too much this stochastic system, so they prefer to work with deterministic system, and the associate deterministic system, which contains these two equations, is the following one. Okay, so it's what is called in infield game the master equation. So you recognize, so U is a function of time, position, and measure. Okay, and this satisfies a nonlinear equation of this form. So you recognize here the effect, the first effect of the common noise, so through the Laplacian of U respect to the space variable. The Hamiltonian, which was here, is again here. The F is here, okay? And there is an interaction term, which is the effect on the value function of a player of the action of the other player. So this is the difficult part in this equation the first difficult part in this equation is this non-local term, okay? Which you see, somehow you recognize the effect of the other players through their optimal strategy here, okay, so which is this term, okay, and then there is a full term of second order derivative coming from the common noise, okay, which is you can see here also. Okay, so you might be surprised, but actually people in economy, some people, I mean, not all, but working on heterogeneous agent model, look at this kind of equation and try to understand how manipulate that, and how to play with the noise to understand stuffs in economy. Okay, so which I don't understand much. But, okay, and what we try to understand with Takis Suganidis is to build solution to this equation, and also solution to this equation. Also, there is absolutely no regularity for the solution, in the sense that the solution U here, despite the Laplacian, is expected to be just, let's say, Lipschitz continuous in space, okay? So you need to give a meaning to this kind of equation. And the reason why there is not regularizing effect of the beta of the Laplacian here is due to the fact that this is common noise which affect all the players together, okay? And so it has very little regularizing effect on the local behavior of the players. Okay. Okay, so what we call dm here is your differential respect to the measure derivative in the extra variable. Okay, so dmu is a vector. Okay, so this is the derivative of Ambrosio Savare. I mean the usual one. Okay. Yeah, yeah, you're right. I mean, the second order derivative here. So you take the derivative respect to m. Okay, this gives you this extra variable y. Okay, and then you take the derivative respect to y, and this gives you a matrix. No, I'm not taking the trace respect to m. Okay, so it's a y is in RD. Okay. And when you take the derivative respect to m, you've got a vector valued function. You take the derivative. Okay, so it's a square matrix. Okay, and actually it's symmetric. Okay, so yeah, so there are all this kind of stuff which pop up. Yeah, this is a factorization. Great, yeah, exactly. Yeah, but except here you need to take. Because of the Brownian motion, you need to take twice the factorization. Okay. Okay, so what I will discuss here is first how we derive this system. So this Milford system. The second is that in order to solve this system, we need to understand what is the solution of the backward Hamilton-Jacobi equation. And here we will see how ideas of optimal transport, like semi-concavity and things like that, pop up. Okay, and then we will build solution to the Milford system. And in the end, I will discuss about weak solution for the master equation. Okay, so let's start with the particle system. So here what I'm going to do is to derive heuristically the coupled system of Hamilton-Jacobian equation and transport equation we saw in the last slide. Okay, so so to do that, I will formally start with a particle system and try to pass to the limit as the number of particles go to infinity. So in this setting, particles are called players or agents. Okay, and we assume that they start from an initial condition which is IID. So Zi is the IID sequence in RD. Okay, and we assume that the state of a player I is given by a stochastic differential equation in which player I controls directly its drift through a control alpha I. Okay, and there is this Brownian motion. So if you look at standard mean-field game problems, you have equations similar to that, but in general, this equation is perturbed by a Brownian motion which is specific to player I. Okay, and these Brownian motions are independent. This is called idiosyncratic noise. Okay, while the difference here is the fact that all players are perturbed in the same way by the same noise. Okay, so the goal of our story was to analyze this kind of problem. Also, in practice, there is often both idiosyncratic noise and common noise. Okay, so I will say a word at the very end about that. But here we look only at the common noise to see the pure common noise to see what is the impact of this noise in the story. Okay, so each player tries to minimize the cost, and here it's please. Yes, that's the point. Yeah. Okay, so when the noise is independent of the, if you have independent noise for each player, okay, you have a very regularizing effect of the noise. Okay, while here it's completely degenerate. You just have one noise, so one d-dimensional Brownian motion, which is the same for all guys. Okay, so that's the difficulty, that's the issue. Okay, and the reason why we do that is that it really pops up in heterogeneous agent models. Okay, so it's not just for fun, or not for fun. No. That's the opposite. In fact, when you have, so I will say a few words about that later on. But when you have plenty of independent noise here. Okay, your system is much more uniformly elliptic, if you like. Okay, and you gain regularity. Okay, and because of this gain of regularity, you can build solution. Here it's not, it's much more complicated because you cannot do that. Okay, so the cost for a player I is of this form. So it's a discounted problem with a discount rate 1 here for simplicity. Okay, so there is exponential minus t. So it's a cost in infinite horizon, which involves a local cost, L, which is basically the Legendre transform of the Hamiltonian that I spoke about in the previous slide. Okay, and this interaction cost, where players interact through their empirical measure. Okay, so this MNIX is just the empirical measure of all players by player. Okay, so the interaction of the player is through this function f. Okay, and in this business, what people try to understand is the notion of Nash equilibria, which means that this is a configuration of controls in which if one player deviates, its cost increases. Okay, so this is what I'm saying here. So we are looking for Nash equilibria, so which are a family of controls alpha bar. Okay, such that if player I deviates, its cost increases of at least minus epsilon. Okay, so it doesn't decrease too much. Okay, so now what we want to understand is so now I'm doing a formal derivation. There are results saying that if you look at epsilon Nash equilibrium, then you end up with the system I'm going to describe. Okay, so but here I'm going to do it completely in a formal way. So what is the intuition behind that? When you pass to the limit as n goes to infinity, you expect that this guy is going to converge to some measure, but this measure must be still random because this measure depends on the common noise. Okay, and so you keep tracks of the common noise. Okay, so this guy is going to converge to some random flow of measure. Okay, and the player have to minimize the cost, taking into account this random flow of measure. On the other hand, the measure must reflect, the limiting measure must reflect the fact that it comes from this kind of empirical measure. So somehow it must take into account the fact that this limit measure is kind of driven by the optimal way of the player play. Okay, so what I mean by that is, in the end, what you expect as the number of players go to infinity is what is called the mean field game equilibrium, which is a pair of control and flow of measure, which are such that both are adapted to the filtration generated by the initial position and the common noise. The alpha bar should minimize the cost. Okay, so very naturally, this is what I said before. Okay, where the dynamics is still given by this kind of stuff. And if alpha bar minimizes the cost, then the compatibility condition, which is the limit of related to the fact that you have the limit of empirical measure, should be this one. Okay, so you look at the optimal path for the players. Okay, and you take the conditional law given the common noise, the Brownian motion here, and this should give you the M bar. Okay, so this is what people in mean field game study when they try to understand what is the mean field game equilibrium, so which is a formal limit. Okay, so without further assumption, one can prove that epsilon Nash equilibria do converge to mean field. Sorry, we can prove that the limit of the epsilon Nash equilibria like that, okay, do converge to minima to mean field game equilibria, which looks very much like that, except that in fact the M bar, the control and the limit measure are no longer adapted to the filtration generated by the common noise, but adapted to a larger filtration. So somehow you need to introduce extra noise in order to when you pass to the limit. Okay, so so what we have tried to do with Takis is to understand in which circumstances you can expect to have strong solution, that is alpha bar M bar adapted to the common noise. Okay, so and this cannot I mean, the difficulty is here to pass to the limit in a stochastic system, okay, in which, in general, you lose the filtration, okay, and this is what I'm going to tell you about. Okay, so in order to do that, I need to translate this expression in terms of value function. So here, in terms of value function. So if you look at the value function associated to a player, okay, so meaning you look at the minimizer of that thing starting from time t and condition to the filtration at wt, okay, you end up with this system of you end up with this Hamilton-Jacobi equation for you. So the value function satisfies the backward Hamilton-Jacobi equation I told you about, okay, while the measure m solves the Kolmogorov equation, which is here. Okay, so this is how we derive this system from this condition. Okay, and as I told you, the Hamiltonian is related to the Lagrangian by this relation. Okay, so the first one who found this system were Lasry-Lyons in the mid 2000. Okay, and it was more analyzed by Lyons in 2010, and then in formal. This was formal derivations. Okay, so and by Carmona and Delarue in particular also, they explain how you must understand this kind of system in this paper. And the first result of existence for this paper were obtained by Carmona, Delarue, and Lacker. And as I told you, actually they prove the existence of weak solution in the sense that the measure m and the value function u are not adapted to the filtration generated by the common noise, but the larger filtration. And with François Delarue, Jean-Michel Lasry, Pierre Lyons, what we proved in this paper is what happens when you have also independent noise. So when the noise here is stronger than the noise here, if you like, if you have a beta prime which is larger than beta here. Okay. And in this case, this system becomes uniformly elliptic, and you have smooth solution. Okay, so classical solution for u and for m. So classical solution meaning classical solution in space, and of course, because you have noise here, okay, you cannot expect to have much regularity in time. Okay, Wilfrid is still not here, so I won't quote this paper. Okay, so let me now tell you how we solve this kind of problem. And in order to solve this problem, what we are going to do is to make a change of variable. Okay, so the reason why is the fact that it's extremely difficult to have estimates on this function v. Okay, and therefore we are going to make it disappear through a change of variable, which is just looking at the solution u bar m bar. Okay, and making this transformation. So you apply the common noise to the x variable. If you do that, you can prove, at least formally, if you have a classical solution to the previous system, that the new variable, u tilde and m tilde, solve a system in which, okay, so for the Kolmogorov equation, the noise has disappeared, almost, because the noise is hidden in the Hamiltonian. So the Hamiltonian is random, okay, so it depends on the noise. And in which the noise has also disappeared here for the Hamilton-Jacobi equation. Okay, so previously you have it here and it had disappeared here. Okay, to the price to get a random term, which is a martingale term. Okay, so we end up with this system. So this is formal derivation. Okay, what we are going to prove now is that this system has a solution, and then justify this solution after the transformation by looking at the master equation, okay, by proving that this kind of system gives me the correct solution to the master equation. So also I'm not looking at the correct system, okay. In the end, I will have a correct answer. So this is what I just said. The only point also I won't discuss here because of time is that, in fact, there are two reasons we are looking at this system. Also, it's not the correct one. The first fact is that we can use this system to games with finitely many players. Okay, so but I won't discuss that. And the second reason is that, as I will show you in the end, you can use this system to build solution to the master equation. Okay, so before, let me start with the backward Hamilton-Jacobi equation. So my system here is made of two equations, okay, Hamilton-Jacobi equation and the Kolmogorov equation. So the first goal is to understand how to build solution to this equation. Okay, so if you didn't have common noise, hi Wilfrid. If you didn't have this common noise, okay, you would have a standard backward Hamilton-Jacobi equation, deterministic, okay, and we know that the correct notion of solution, when you don't have smooth solution, is the notion of viscosity solution, okay. But here there is no way to build a viscosity solution for that because of the noise here, okay. So I mean, there is no way. There is no classical way to build viscosity solution for that because of the term here. And in particular, you see that because we want to solve this equation, okay, we need to have a classical gradient in this equation. Okay, so this is what I'm going to explain, is how to build solution to this equation, to the Hamilton-Jacobi equation, in order to build gradient here. How? Sorry? 20 minutes. Okay, so now the backward Hamilton-Jacobi equation. So this equation, okay, so I forgot about the m term, which can be put into the h tilde. Okay, so you have a Hamilton-Jacobi equation, and you want to give a meaning to that. Okay, so there are basically two different theories to build solution to Hamilton-Jacobi equation. So as I said, viscosity solution, which is now the classical one. But before that, for convex Hamiltonian, there was this Douglas or Khrushchev-Douglas approach, which was requiring to the du to be a semi-concave function, and to us that this solution is satisfied in the almost everywhere sense. Okay, so if you just ask the solution to be Lipschitz and satisfies this equation almost everywhere, okay, there is no uniqueness. Okay, and the way to fix this uniqueness issue is either to talk about viscosity solution or to talk about semi-concave solution. And it turns out that, very surprisingly, for this kind of equation with noise, okay, this Douglas approach works perfectly. So when you have you saw in our transformation, the noise appears only here and through the Hamiltonian, okay, which is just a function which is adapted to some filtration, okay, and if you had an extra noise here, if you have a diffusion term here, okay, then you would be in the framework of Peng, okay, who proves that there exists classical solution to this equation. Okay, so what we're doing here is slightly more difficult because we remove this extra diffusion term, and we end up with an equation which is typically of first order, but with a random perturbation. Okay, so this has been studied recently by Q and Wei. Okay, but the notion of viscosity solution involves a derivative in the path space. Okay, while here we really need this du to exist in a classical sense. Okay, so let me say what is a viscosity solution. What is a viscosity solution to this equation? So the key point is to ask for bounds, uniform bounds on the solution, uniform bounds on the derivative, so globally Lipschitz, okay, in space. The fact that the martingale term is bounded, but mostly the key assumption is you require that the function u is semi-concave in space. Okay, so this second order derivative is bounded. Okay, and this is okay. So this is the key idea of Khrushchev for conservation law and Douglas for Hamilton-Jacobi equation with convex Hamiltonians. And it turns out that this kind of idea propagates here, works, is sufficiently robust to take into account this kind of term. So the process here is a continuous martingale, and you have this equation which is satisfied in the almost everywhere sense, in the sense that if you integrate in space, if you integrate in time, okay, you have that the equality holds almost everywhere. Okay, so under suitable assumption that I skip, okay, we can prove that there exists a unique solution, and it's based on comparison principle. Okay, so it's the kind of miracle here is the fact that you can extend to the stochastic framework the classical Douglas theory for uniqueness of solution of Hamilton-Jacobi equation. So through a comparison principle, okay, which is standard. If you have a sub-solution and a super-solution to the equation, okay, then you have the comparison. And thanks to this comparison, you can prove existence of the unified game system. So we come back to this system with common noise, okay, and okay, I skip this because it's quite redundant with what I said. So what is the solution? Again, it's a solution which is bounded. So what is important here also to underline is the fact that to be a solution means that this equation must be satisfied in the previous meaning. Okay, so the solution of the backward Hamilton-Jacobi equation, but also the fact that because you know that the solution, because you know that you have semiconcavity estimate on du, you expect that the measure m, if it starts from an initial configuration which is which has L infinity density, okay, then this density remains bounded. Okay, so this is exactly what we ask for the solution. Okay, so the solution has a L infinity density. Okay, and you have again the semiconcavity estimate. The equation, the Hamilton-Jacobi equation is satisfied in the almost regular sense, and you have in the sense of distribution the continuity equation which is satisfied. Okay, so remember that all these guys, and of course I didn't underline it enough, but all these guys are adapted to the filtration generated by the underlying Brownian motion. Okay, okay, and under suitable assumption that I won't discuss, but especially under suitable monotonicity assumption, okay, you have a unique solution to the infinite game system. So what is new here is the fact that the solution is really adapted to the, is unique for one thing, which was not the case in the paper by Delarue and co-authors, and it is also adapted to the filtration generated by the infinite game system. Okay, so let me start the last part of the talk where we are going to use this this solution to the master equation. Okay, so again, what we have in mind is that in economy, they are working on this equation, okay, and the goal is to give a meaning to this master equation. Okay, so let's come back to this equation. Okay. So again, you recognize the Hamiltonian from the Hamilton-Jacobi equation, the interaction terms, okay, which is the bad term which makes the equation without comparison principle, okay, and strongly nonlinear and strongly non-local, okay, and the impact of the common noise, which here, of course, it's linear, okay, so it's linear in terms of U. Okay, so this kind of equation has been first studied formally by Pierre Williams, and then there is a nice paper by Gangbo and Siek in 2015, sorry, where they study what happens when beta equals 0 and in short time horizon. And the first papers dealing with problems with beta equals 0 but with idiosyncratic noise, so it adds some terms here, okay, was by Chassaigneux, Crison, and Delarue, and we revisited this kind of question with the paper with François Delarue, Jean-Michel Lestre, and Pierre Williams to deal with this kind of equation, but with an additional idiosyncratic noise, which gives you a classical solution to the equation. Okay, so it becomes kind of uniformly elliptic in space in the x variable. Okay, and therefore you can build classical solution here. While in our setting, we are completely unable to build classical solution because the noise is too degenerate to have a classical derivative in x of the function u. Okay, so in space. So there is a huge literature on this kind of problems that I won't discuss here, and it's related also to Hamilton-Jacobi equation in infinite space dimension. I just quoted a few recent contributions on the story here. Okay. But here it's not a Hamilton-Jacobi equation. You have to keep that in mind. There is no, for instance, there is no comparison principle, okay, which makes the story quite complicated. And in particular, so I said that the function f was supposed to satisfy some kind of monotonicity condition. Okay, without this monotonicity condition, nobody really understands the meaning of the equation. And in fact, what is expected is that the function u should be even discontinuous. So here I'm working in a case where f is monotone, so satisfying this monotonicity assumption. Okay, in which case we expect at least u to be a continuous function of m. Okay, so that's it. Okay, so the starting point, so what we're going to do is to build what is called a monotone solution to this equation. So keep in mind that we are going to assume that u is continuous, okay, but not smooth in space. Okay, so to give a meaning to this, so to give a meaning to give a definition of a generalized solution, it's always cheap. You can always do that. The difficulty here is to prove the uniqueness of the generalized solution. And to do that, we are going to use ideas of Charles Bertolucci for monotone solutions. So the starting point is a nice remark by Lyons, which is the following. If you take two functions defined on space and measure, okay, and assume they are continuous, and Lipschitz in the first variable, okay, and assume that they minimize, assume that this inequality holds for any m and n prime. So it's a monotonicity inequality, okay, which says that you require that u of xm minus u2 of xm prime integrated against m minus n prime is non-negative. Okay. Then it's a simple exercise to check that, in fact, dx of u1 is equal to dx of u2. Okay, so which gives you a kind of uniqueness. So if you can prove this kind of inequality for any n prime, this gives you a kind of uniqueness for the derivative. Okay, for us, it's important because this derivative is really the leading term for the Fokker-Planck equation. Okay, so what we are trying to identify is really the derivative like that. So if you see Lyon's result, in order to prove uniqueness, what you have to prove is this kind of inequality. Okay, and in order to prove this kind of inequality on two solutions U1 and U2. Okay, and to define the notion of weak solution for U1 and U2 is, the idea is like in viscosity solution, what you are going to do is to say, okay, if I minimize this quantity, okay, respect to m and n prime, okay, this means that in particular, I minimize respect to m this quantity with n prime fixed at the minimum, okay, and in this case, U2 and m prime are given, okay, and so you can transfer, you can use this kind of stuff to try to identify the kind of equation that should satisfy U1 at such point. More precisely, so I replace U2 by some function phi of x, m prime by some measure m tilde, and I look at minima of this quantity. Okay, so this is what we would do if you wanted to minimize this kind of stuff and use the fact that you are at a minimum. Okay, so you minimize exactly this kind of quantity and try to translate into the test function phi and the test measure m tilde the fact that you are at a minimum. Okay, so I'm going to write that in the simplest case where you don't have beta, okay, and then I move to beta. Okay, so for the first master equation, which takes a slightly simpler form here, so you only keep the bad term, which is the interaction between the player, which prevents the equation to have a comparison principle, okay? And assume that you have a minimal classical solution to this equation, and assume that you are at a minimum of this kind of stuff, of this kind of expression given phi and m tilde. Okay, then you can prove that that phi and m tilde do satisfy this kind of relation. Okay, what it says, it says that u evaluated against m naught, so m naught is the minimum, and minus m tilde plus the bad term, but here I'm assuming that u is smooth, classical solution, so dux is well defined, okay, integrated against, again, m naught minus m tilde, plus this quantity, which corresponds to this square. Okay. But here, in this this quantity I had dmu, while here I don't have dmu. Okay, so I lose the derivative just by writing the optimality condition by saying that this guy has minimum at m naught. Okay, and because it has a minimum at m naught, this gives me dmu in terms of the difference between dxu and dx phi. Okay, so I can replace dmu by this quantity. Okay, and again, it's above f of m integrated against m naught and mt. Okay, so the good point of this definition is that even if you have a classical solution, okay, you can replace the term for which you don't know that you have a classical derivative by this kind of difference. Okay, and Charles proved that this allows to define weak solution, but he was working in a framework where the state space was compact. Okay, and when you have idiosyncratic noise, in the sense that the solution was smooth in X, but here we work with solutions which are not smooth in X. So in this case, we need to be a little bit careful because the function nu, which is going to be Lipschitz, this term is defined almost everywhere. Okay, and you integrate against measure, so you have to be a little bit careful. Okay, so this is what I'm going to explain next. Hello. Okay, so this gives you the definition that I suggested. So we say that U is a monotone solution of my equation if it's Lipschitz continuous semi-concave in the space variable. Okay, and if you fix phi and m tilde plus some extra penalization term like that, then at minima, at the minimum m naught of this quantity, okay, you have this inequality, which is basically the inequality I wrote before, except that there is this penalization term that you pay here. Okay, so, and what we are able to prove is that under suitable assumption, there exists a unique solution to this kind of equation. So, the difficulty, of course, is to cook out the good penalization term, which turns out to be this here, okay? So the fact that you can penalize by the infinity norm of m is related to what I told you about the mean-field game system, in which the measure m could be taken as absolutely continuous with bounded density, okay? So it reflects, it can be, you can see it here. So this is the reason why it's this crazy idea to put an infinity penalization on m makes sense, okay? So the equation is compatible with this infinity penalization. Okay, so it turns out that if you assume relatively mild assumption on the data, the stronger one being that the function f is monotone, then you have a unique monotone solution to the equation. And existence, I will tell you a little bit when I discuss about the second order master equation. So let me skip this and now come back to the second order master equation. So we would like to do the same when beta is not zero. So when you have all these terms, this second order derivative, which pop up. And you probably know, but if you are working on Hamilton-Jacobi equation, for instance, for viscosity solution, in infinite dimension, there is no way to build a second order derivative. So you have to do something which is a little bit involved. So first thing is that you have to work in a Hilbert space, okay, and second, you have to approximate the second order derivative by finitely many derivative, if I may say so. You have to come back to finite dimension in order to use viscosity solution theory, okay? And this is what we are doing here, okay, and we follow here the work by Lyons. So the first thing is to work in a Hilbertian setting, and then to do this machinery of finite dimensional approximation. Okay, and here I must say that for Hamilton-Jacobi equation, this has been done by Wilfrid in a paper with Spherical. So the idea is to work in a space of random variables instead of measure. Okay, so I'm going to replace the measure by random variables, okay, and define the function W. So if I have a function defined on the Wasserstein space, I extend it to the space of random variable by defining W tilde of X, where X is a random variable so an element of L2, by W of the law of X. Okay? So what you can prove, for instance, is that the Wasserstein derivative of W is related to the gradient of W tilde, okay, by this kind of relation. Okay, so because of that, you can replace the second order master equation, which is here, by an equation stated now on L2, okay, which takes this form, which is what you can recognize almost all the terms. Okay, the only a little bit surprising term is this one, where Ek is just the constant random variable taking values Ek, where Ek is the basis of RD. Okay, so this term becomes that. Okay, and then you play with this Hilbertian framework to define what is a monotone solution. So I won't discuss it because it's a little bit long, but this is the same kind of idea. You put a penalization on the density of the measure with which you work, okay, and you end up with this kind of inequalities that should satisfy, okay, so kind of generalized derivative of the function which is here. Okay. It turns out that within this framework, we're able to prove that you have at most one monotone solution. Okay, so again, the uniqueness holds for dxu and not. We are missing a map depending on M omni. Okay, so but again, it's for our purpose, it's enough. And I finish on that. For the existence of a solution, okay, what you do, you come back to the mean-field game system that I described first. Okay, so the key idea is that, so remember, the mean-field game system we solved was not the correct one. Okay, we made a transformation. And solved something which a little bit transformed. So, and we are not able to come back to the initial formulation because we have not enough control on the martingale part. Okay, but nevertheless, if you build the function u of x m naught by using this mean-field game solution, the solution of the mean-field game system, okay, you end up to build a monotone solution to the equation. So in the end, this shows you that u, the second order master equation, has a unique solution, okay, generalized solution, provided some assumption that I did not discuss. Okay, so let me conclude briefly about what we have done since this work. So recently with Ben Seeger, which was supposed to be a postdoc of Pierre Cardaliaguet and myself in Paris in 2020. Okay, we could not come much in Paris, but so we generalized this approach for the mean-field game to what happens for degenerate idiosyncratic noise and common noise, okay, which turned out to be a little bit subtle. And what is completely open is that is precisely when you keep the idiosyncratic noise and the common noise to build monotone solution, because the Lyon's framework of random variables is very beautiful to deal with the common noise, but it's completely, I mean, apparently it doesn't fit at all cannot allow to take into account the degenerate idiosyncratic noise. Okay, and what we don't know at all in this story is that to pass to limit is to show that the limit of the mean-field game system, the Nash system, converge to what I've described here in this talk. Okay, thank you very much.
Thank you, Pierre. Is there any question? Well, this is not the case. So thanks again. So we have now the coffee breaks nearby. We resume at 11 with the lecture by Wilfrid Gangbo, who in the meantime appeared. Now we resume with Wilfrid Gangbo, and Wilfrid will speak about on some optimization problems involving matrices of large sizes.
Thank you. Yes. It is a great pleasure to be back to Pisa after that many years. You cannot hear. Can you hear now? Okay. Yes, it is a pleasure to be back to Pisa after many years. And I would like to thank the organizer for the invitation. I would like to also apologize for not attending my talk. I was trying to minimize the transportation part, and I have the wrong sign in front of the course, so it maximized. So my talk is based on a joint work with David Jekyll, Kyung-Sing Nam, and Dima, Shilai, Tenko. Okay, so let me start with some notation. MNC is the set of n by n matrices with complex entries. And MNC SA is the set of matrices which are self-adjoint, which means that MJI bar is MIJ. So, to illustrate what I want to talk about, I am going to start with a finite dimensional model, and then I will go to a more general model. So, I am going to choose a trace on some arbitrary set. And first, I would like to tell you that there is a unique trace. So there is a theorem which is more general than the following theorem. Fact. There is at most one linear map lambda from M and C to C, such that lambda of 1 is 1. So this is the identity matrix. Lambda of AB is lambda of BA. Lambda of A star A is greater than or equal to 0, and equality hold if and only if A equal to 0. And it may look strange that I say there exists at most one map. We have the solution is given by lambda A equal to 1 over n, with sum j from 1 to n, a j j. which I am going to call this the normalized trace of A. So I want to look at a bigger set, which are infinite dimensional set, and one can state the same result. The same result is known. So later, I am going to let n go to infinity. And the best way to describe this set when n goes to infinity is I am going to define later what is a Poincare algebra. So it comes from the fact that in the past decade, when people were studying random matrices, and they let the size of the matrix go to infinity, the right object to describe the limit is a Feynman algebra. So here, my Hilbert space is H equal to Cn, and the set of bounded linear operator on H is MnC. And later I am going to replace H by an arbitrary Hilbert space. You mean here? Yes. No, I introduced this set and that set. And here I am working on the bigger set. Okay. So let M1, Mn, Md. So D is going to be fixed. It is not going to vary. Be in MnC. And let N1, Nd be in Nmc, possibly N is not M. I want to define what it means that M equal to M1, Md is equivalent to N equal to N1. Nd. So this means that I am going to define the law of M when I apply to any polynomial. So C x1 SD is the set of non-commutative polynomial when I compute the trace n of p of x, p m, it must be equal to the trace m of p n for every p, which is a non-commutative polynomial. So here, instead of working with a smooth function of d variable, I'm working with a polynomial. And I define my equivalence relation this way. So for example, assume that M is N. Then M, the matrix, is equivalent to N if and only if there exists a unitary matrix such that Mj equal to U star Nj, U, for every J. And I may be making this mistake often. This must be self-adjoint. Self-adjoint. And of course, the unitary matrix is not self-adjoint. So if you take a D equal to 1, this means that M and N have the same eigenvalues. But when D is strictly greater than 1, you cannot just describe a thing in terms of eigenvalue. So the idea of Bian and Voiculescu is to define a metric which on the set of classes of equivalence. So I am given a class of equivalence of M, a class of equivalence of M prime, and I want to decide when is M close to M prime. I want to write an explicit formula for that. So inspired by what happened in optimal transportation, I want to replace this object by law. So I want to go to Eulerian coordinate. Definition. Given R greater than 0, we define sigma dr, but my d is always fixed, to be the set of lambda from C S1 SD to C, such that lambda of 1 is 1, lambda is linear, and if I compute lambda of Si1, Sik, so I take any monomial which consists of this k variable, which may be equal or not equal. This is less than r to the power k. So this will be the analog of L infinity if I was working with measures. If you take lambda naught, lambda 1 in sigma dr, pi lambda naught, lambda 1, is the set of gamma, which are in sigma 2d r. So I am going to double the number of variables such that if I compute gamma of p tensor 1, I get lambda naught of p, and gamma of 1 tensor q, I get lambda 1 of q. This is true for every p in C S1 SD, and q in C X D plus 1 S2. So whenever you write the monomial Si, it is always understood that Si star is Si. So you endow the set of non-commutative polynomial with a law star such that this holds. So the distance square bien Wescolescu between lambda naught and lambda 1 equal to the infimum over gamma in pi of lambda naught, lambda 1, gamma of the sum j from 1 to n, Sj minus Yj square. So observe that because Sj and Yj are self-adjoint, this is Sj minus Yj multiplied by Sj minus Yj star, and so this is non-negative. So a disclaimer, I am not doing any optimal transport. So don't ask me what I am transporting. I done enough optimal transport this morning for 5 minutes. However, this distance is related to optimal transport. I am going to mention in some particular case. I'm going to mention that later. So when you look at this minimization problem, this is a minimum because pi lambda naught, lambda 1 is a compact set. For the pointwise convergence. And so there is no concern about existence of a minimizer here. Now, I am going to go to Lagrangian coordinate. It is the analog of Lagrangian coordinate, which Bian and Voiculescu already done. So definition. Let H be a Hilbert space. We call calligraph A subset of a set of bounded operators on H, a von Neumann algebra. If A is closed under the weak operator topology, A contains the identity, and A is a star algebra. So it means that I have an algebra with an evolution which satisfies the property you are going to write A plus B star is A star plus B star. A star 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 is A. Lambda A star is lambda bar A star. So this is the property which you require. If x1, Sn are in A, and I am assuming that A is a von Neumann algebra, and are self-adjoint, the law. So people refer to V as the non-commutative law. Of x is lambda x which is defined from C S1 SD into C, defined by lambda x of a polynomial P. This is the trace of P of x. So if I take any polynomial for every P, non-commutative polynomial. So if I take any polynomial P and apply P to x, I get an operator in my von Neumann algebra, and I take the trace. So where did this trace come from? I have assumed there exists tau from A to C linear such that tau of the identity is 1, tau of AB x AB is tau of BA, tau of A star A is greater than 0, and equality holds if and only if A is 0. So when I am given a Feynman algebra, I may not have a trace. But if I have a trace, there is only one trace from the remark I made at the beginning. But we are going to assume that here we say that the trace is unital, tracial operator, faithful. And we are going to assume that it is normal, which means weakly continuous. Okay, so whenever all these properties hold, we call A, tau, a tracial W star algebra, or a tracial Feynman algebra. So the following result, which is at the first glance surprising, but the proof is easy to give. Theorem. This is part of what is called the GNS construction, Gelfand, Neymark, and Siegel. Given a non-commutative law, given lambda in C dr, there exists a W star algebra, A, tau, I am going to call it tau A, such that and X in A, such that lambda is lambda X. So this is the analog of what you have in probability measure. Whenever you are given a measure, there is a random variable which has that as a law. But one of the weaknesses in free probability is you have no reference Feynman algebra. It is not like in measure theory where you can choose a reference measure to find all the random variable for any arbitrary measure. And here is an idea of the proof. And for P, Q, non-commutative polynomial, S1, SD. I am going to define what I hope will be an inner product, PQ, lambda. This is lambda, P star Q. But it is possible that the set n lambda, which is the set of P in C, S1, SD, such that the norm lambda norm equal to 0, it is possible that this set is not reduced to the null vector, but this set is an ideal, which means that if I take any element here, if I multiply it by any other element there, the product will belong here, my other thing. So you take H, your Hilbert space, you take C, S1, SD, you quotient by n lambda, and you close this with respect to the inner product. And you have your Hilbert space. You are going to set Si of P to be the class of equivalence of P little Si, and you check that this gives you the random variable, the non-commutative random variable. Now, we can express, it was already done by Bian Voiculescu. We can express the distance square Bian Voiculescu between lambda naught, lambda 1. This is the infimum over Feynman algebra, the infimum over x, y in A, D, self-adjoint. And you minimize the norm x minus y square, the tau A norm. So look, this problem like that, if you try to use any direct method of the calculus of variation to find the minimizer, this is a nightmare. However, I have a minimizer there. I stated this theorem telling me that whenever I have a law, there is a non-commutative random variable associated to it. And so I am going to apply that to the gamma optimal there, and it is going to give me the optimal x, y. So the question which people in operator theory has been interested in for a while is when is there an optimal map? Can I write that y is T composition x for some x? So a paper by Alice Guillaume and Dima Schlachenko 2014, Guillaume. They prove that there exists lambda naught, lambda 1, and a map which transport lambda naught to lambda 1. In fact, they show that there exists a map which is a gradient of a convex function, but they could not show that this is the optimal transport map, and the measures were very specially chosen. In 2021, there is a paper by Jekyll, Shlachenko, Lee, Shlachenko, showing that for every lambda naught, if phi is convex with bounded second and third derivative, the push forward of lambda naught is optimal. Transport. And they check that these fall in that category, which means that they answer the question of Guillaume and Shlachenko. So here is the result I would like to state. Oh, before that, there is something very important, which is, I would say this is our main contribution theorem. There exists W, a collection of Riemannian algebra such that any two elements of W are not isomorph. Every threshold W star algebra is isomorphic to an element of W. Okay, so it means that we look at a complete list of threshold Riemannian algebra, and we don't want to repeat them. So we are going to keep one representative, and the second part is saying that we cover all of them. So definition, a collection of function Fa from A to negative infinity plus infinity is called expectation convex. If whenever A and B are in W, and I from A to B is a threshold embedding inclusion, we have a compatibility property FA equal to FB, composition I. So we can go from one function to another, but more importantly, FA composition, the adjoint of I is less than FB. This is a Jensen inequality type, which in finite dimension you have, and FA is convex. Is convex. So this is the main ingredient which allows us to prove a duality result. And I'm going to finish in 2 minutes. Theorem. Given lambda naught, lambda 1, non-commutative law, let there exist A, tau A, Riemann algebra, X, Y, self-adjoint, such that lambda naught, lambda x, lambda 1 is lambda y. This is like a repetition. X minus y. L2 tau square is the Bian Coequalescu distance between lambda naught, lambda 1. And finally, if we set St to be 1 minus t x plus t y, which is the displacement interpolant, for any t between 0 and 1, there exists an optimal map from St to x. But more importantly, we can characterize there exists FA, GA, expectation convex, such that the Lejeune transform of FA is GA, and the distance equal to So let me write xy equal to norm tau equal to f of x plus g of y. And you can see that I have rewritten what is there. If you expand this, you have s squared plus y squared. S squared depends only on lambda naught, y squared depends only on lambda naught. And so you are maximizing negative this. And you can characterize the optimizer this way. Furthermore, a necessary and sufficient condition to be an optimizer is if there exists an E-convex pair of function. I'm going to stop here.
Thank you, Wilfrid. We have time for a very short question, if any. Jan.
Yes. Yes, so because this function fa, they are convex. Maybe I forgot to say it. For each a, fa is convex in the classical sense.
So other questions? You had one.
No, in fact, we can show the following important thing. We can show that even if I start with two laws, which come from finitely, which come from matrices, there are examples where the optimal, the Feynman algebra will be of infinite dimension. And so trying to hope that you work on infinite dimension and you get optimality, that is not correct.
Okay, we can stop here. Let's thank Wilfrid again. Okay, let's proceed with Lorenzo Dello Schiavo, and he will speak about Dirichlet-Ferguson diffusion.
Yeah, thank you very much to the organizers for the nice invitation to be here today. Of course, it's a very great pleasure. I apologize for the technical inconveniences, but let me start right away with a bit of setting. So throughout the talk, MGM will be a closed Riemannian manifold. By closed, I mean compact and without boundary. The dimension will be always strictly larger than 1. In particular, the unit circle is excluded. I'll point out where this is used, of course. And M will always be the volume measure. Since our manifold is closed, we can always assume that M is normalized, so to be a probability measure. PM will be the space of all Borel probability measures on M. And as most of you know, this inherits a natural, say, Riemannian manifold structure from the underlying base manifold. There are a certain number of concepts that most of you are certainly familiar with. One is the L2-Kantorowicz-Rubinstein distance or Bastlein distance W2. There's concept of geodesics, the gradient, an exponential map, and even of a Levi-Civita connection. So there's really a rich Riemannian geometric understanding of the space PM. Since, again, our manifold is compact, this coincides with P2, the Bastlein space. Of course, there's also something that is missing from this picture if we want to understand PM as a Riemannian manifold. And what is missing is a Riemannian volume measure. Now, one should have some agreement what Riemannian means. I'm not going to go into details about that, but basically a volume measure that is somehow compatible with a metric structure, so at least with a distance. Now, provided that such a measure exists, of course, one could also be interested in saying what is the Brownian motion on this space. which would be a canonical stochastic process which has P as its invariant measure. And now throughout the talk, what the goal will be is to propose a candidate for such a measure P, to show that this candidate, which will be the Dirichlet-Ferguson measure from the title, has natural properties and allows for the construction of a Brownian motion, which can be completely characterized. Why does one want to do this in the long term? So what are the long-term goals? Well, there are several. Of course, one would be to study stochastic PDEs on manifolds. And the idea, this is maybe an idea that dates back already to von Renesse and Sturm, is to say, does there exist something that we can call stochastic autocalculus? So autocalculus is a way of lifting partial differential equations from the base space to gradient flow equations on the Bastine space. The idea is there is a trade-off between a complicated equation on a finite dimensional space and a simpler because the first order equation on an infinite dimensional space. One could try to do this at a stochastic level, and one could try to do this in reverse. So if I say I have something that I want to call the Brownian motion on the Bastine space, and if I can beam down this to the manifold, this might be, by definition, say, the stochastic heat equation on the manifold, in analogy with the idea that the gradient flow of the entropy is describing solutions to the heat equation. There's also relationship to other stochastic PDEs, for instance, the Dean-Kawasaki equation, which will appear later on. A completely different setting now is one might be interested in more geometric study of Bastine spaces that includes concepts of curvature. It's known that Bastine spaces inherit synthetic sectional curvature bounds, but if you also have a measure, then you can ask slightly more sophisticated question about synthetic Ricci curvature bounds. For instance, you can ask if this space satisfies the Bakry-Emery condition or the RCD condition. I should point out that in dimension 1, so when M is dimension 1, there are already some negative results in this direction for specific measures, but really not much is known, because one should study this basically measure by measure, so for every choice of P. And finally, there is one motivation which will be my point of view throughout the rest of the talk, which is the representation of large Lie groups. What do I mean by this? Well, take psi to be a diffeomorphism on M. Then psi maps points to points. But on the first level of this sort of tower, psi push forward maps probability measures to probability measures. And one should note that if M is the Riemannian volume, then psi push forward M is equivalent to M, in the sense that these measures are mutually absolutely continuous. Of course, there is one higher level still when one considers psi push over, which is just a push forward of this map. And one might ask the same question. So our measure P is such that psi push forward is equivalent to P itself. Now, if this is true, then this map, psi into psi dot, where this is psi dot, so just push forward of measures, this defines a quasi-regular representation of the group of diffeomorphisms on M in L2P. Why is this important? Because with this understanding, one can construct a Dirichlet form, which would be the Dirichlet form associated to what I would like to propose as candidate for Brownian motion. Now, before doing the construction at the level of Bastine spaces, let me start with a very simple toy model. Toy model will be the Euclidean space. The idea is to construct a geometric diffusion starting from the action of a Lie group on some space. So G is a nice Lie group. Say Rn, so groups are in blue. Say Rn, the group of translations of Rn in green. This is just the Euclidean space. The group comes with an algebra, this fractor G. Again here, Rn. And this would be just the tangent space at the origin or at the identity of the group. And also comes with an exponential map. The exponential map here is just the identity. We apply a vector to move by translation. Next, we need a space. Our space will be, say, a standard, for instance, probability, but also sigma finite would work. For instance, probability space, say Rn with a centered Gaussian measure. Assume that the group is acting sufficiently nicely. Again, here it's just the action by translation. And assume that we have a reference measure P, which is G quasi-invariant, which means precisely this, that the image of P via the action is always equivalent to the original measure. This is the case for the standard normal distribution on the Euclidean space. Next, we need a gradient. And how can we define a gradient? Well, suppose we are given at each point omega in our space a Hilbert space, which is also a subspace of the algebra. For instance, the standard tangent. Then we can define for sufficiently smooth functions u a directional derivative, which is just at a point omega in the direction w. W is a tangent vector, so it's an element of G. And this is just the derivative of time 0 of u computed at the shift by w, where the shift is given by the exponential. And of course, in the Euclidean setting, this is a standard derivative. And this defines a gradient, which is the unique object that satisfies this relation just by Riesz representation. So by Riesz representation, there exists a unique function with values in the, say, tangent bundle that when we take the scalar product with the direction gives us the directional derivative. Of course, in the Euclidean space, this is the standard gradient. Once we have all these objects in place, what we can do is define a Dirichlet form in this way. This is EUV, just the scalar product of the gradients at each point in the tangent bundle. And provided the form will be closable, this is of course the main technical issue. One needs to show that there is some well-posedness in this, and well-posedness here means the closability of this form. Then the abstract theory of Dirichlet forms states that there exists an associated process, which in the example will be the Ornstein-Uhlenbeck process. Now the idea is to do this very construction on Bastine spaces. So let me start with what the group should be. Now there is, please. Yeah. Closability as a functional on the Hilbert space L2 of P, as a quadratic functional. No, it's just a topological condition. It's just the Hilbert space closability of a quadratic function. Any more questions? Yeah. Very good question. This will depend on whether we agree that P is canonical. So the measure that I'm going to propose in the following has some specific properties that I would argue in a sense state that this is a good reference measure, canonical reference measure. But of course, this is sort of based on a mutual agreement that this is the case. Canonicality is sort of transferred from the measure to the process. More questions? Okay, let me go on. We need a group and an algebra. The group again will be the group of diffeomorphisms. The algebra is this X infinity, the algebra of smooth vector fields, with a standard Lie bracket of vector field as the commutator. And the space will be just the Bastine space. Now the exponential is the flow of a vector field. This is a one parameter group of diffeomorphisms that exists for all times because our manifold is compact and without boundary. Next, we need a tangent space. This is occasionally called the pseudotangent space to PM. It's been maybe first considered by Gangbo, Kim, and Pacini. And it's slightly larger than the usual tangent space in the sense that it is the whole closure in the L2 norm of mu of tangent vector fields, not only of gradient type tangent vector fields. This is more or less irrelevant for the rest of the construction. It's just a matter of a point of view. Why is this so? Well, because when we define the directional derivative of sufficiently nice function u, we compute this as the time derivative of u computed at the shift by the flow of a vector field w of a measure mu. But now on the base manifold, the shift is tangent at first order at t equals 0 to the geodesic flow, so the exponential tw. And this tangency is preserved when lifted on the Bastine space, so this means that these two derivatives are the same. And if you want, this is the diffeomorphism point of view, and this is the standard Wasserstein geometry point of view, where gradient type is what matters. And again, a gradient, this will just be the Otto's gradient, for those of you who are familiar with it, will just be induced by Riesz representation from the directional derivatives. Now that we have the geometry, we need the measure. And the measure is, what I would propose as a candidate, is the Dirichlet-Ferguson measure. I'm not going to state the definition, but I'll phrase this integral identity as a characterization which you can take as a definition for the purpose of the talk. Bit of notation: if mu is a measure in PM, then mu x will always be the mass of mu at x, and mu x r will be this convex combination. We take 1 minus r times mu, and then we sum r times the Dirac at x. Now, the Dirichlet-Ferguson measure, for the purpose of the talk, is the unique probability measure satisfying this identity. What does this mean? Well, you have some random functional integration with respect to mu of a function u that depends on 3 parameters: a measure, a point on the base space, and the mass of the measure at that point. And then the formula basically says that in expectation, so when you integrate out the randomness, you can trade off this random functional with a deterministic one, which is the integral with respect to the volume measure. The cost that you pay is that, of course, now you've taken this convex combination, so you need to average over the convex combination parameters. So there is one additional integral here. This is an integral on the unit interval 0, 1, which averages over this parameter r, which appears here at the mass of the Dirac measure. Now, one can interpret this characterization in terms of Bayesian nonparametrics, which is where these measures first appeared, but also as a Mecke or Georgi-Nguyen-Sessin type formula, which means that there is a statistical mechanics interpretation for this measure. Now, why is this measure canonical? And hopefully this will answer the question from before. Well, first of all, it has some nice universal properties. It satisfies some functoriality condition with respect to some diagrams, which relates it to the construction. This construction works whenever x and y are, say, measure spaces, but even Polish spaces where you have a measure m assigned. Also, it can be constructed as a projective limit along a natural sequence of marginalizations. This is, in fact, the original construction by Ferguson. And the idea is as follows. Take your space X, partition it into n pieces, and then take this map, mu into mu x1 up to mu xn. Now, since mu is a probability measure, this is an element of the standard simplex. So if you give me a natural distribution on the standard simplex, and you're able to take the limit as n goes to infinity, then you will recover Dirichlet-Ferguson measures. The natural distribution on the simplex is the Dirichlet distribution on the simplex. And this is canonical because if you want, for instance, it is the Haar measure of the standard group structure of a unit simplex. Of course, this measure is somewhat nice, but not exactly as one would expect. It is atomless with full support. This is what you would require of any candidate for a volume measure. But it's concentrated on measures that are purely atomic and that have infinite many atoms. So basically, it's concentrated on this infinite product of locations of the points times the interior of the infinite simplex, which accounts for the masses of the points. So basically, dm, almost every measure mu looks like this, where in this picture, say, the unit square is our space x. And there is a characteristic scale, because you can put a parameter beta here in front of m, a real parameter. And the characteristic scale of an atom with highest mass is beta inverse. This beta is supposed to remind you that there exists a statistical mechanics interpretation where beta can be understood as an inverse temperature. Okay, now that we have the measure at hand, what we want to do is do the construction of a Dirichlet form. Again, we have the geometry in place, we have the measure in place, but still we need a core of sufficiently nice functions, which we want to regard as the equivalent of smooth functions. And as this, we choose potential energies and the algebra of cylinder functions generated by potential energies. Potential energy just means that we regard a smooth function as a function of a measure by writing f star of mu mapping to the integral of f in d mu. And then we construct basically the outer algebra obtained by composition of arbitrarily many, but finally many of these functions with a smooth function on some Euclidean space of high dimension. Now, these functions are extremely nice because they are, of course, continuous, and one can compute explicitly Otto's gradient on this function. So one can compute explicitly this form. The main theorem is that this form is actually closable. And once you know that this form is closable in the sense of L2 closability, then the standard theory of Dirichlet form, however abstract, tells you that there exists an associated diffusion process. Let me call this mu. And one can characterize the process in terms of properties of a form. So the form will be regular, recurrent, strongly local, symmetric, which means that our process also will be recurrent, in particular reversible, on the space of probability measures. Now remark, there is a very recent work by Massimo Fornaciari, Giuseppe Savare, and Giacomo Enrico Sodini, And combining their result, which is extremely more general, with the closability of this form, one obtains the identification of this energy above with the Giga energy constructed from the Base-Stein distance W2 and the Dirichlet-Ferguson measure dm. The results, in fact, apply for any measure in place of dm for which you know closability a priori. Now, why is this important? Well, for two reasons. First of all, because you know, you have now a characterization of this measure, of this Dirichlet form, that depends, sorry. Yeah. Yeah. So this is a projective limit over the partition getting finer and finer to the space. It's a kind of a Kolmogorov type construction. Yeah. So this is just the location. The tori is supposed to be the base manifold. Sure. So why is this important? Well, because one can import tools from one theory to the other. Typically, for instance, it is extremely difficult to put your hands explicitly on this object. It is difficult to compute it. But the form is easily computed, at least on cylinder functions. Yes, exactly. On the other hand, it's typically difficult to study properties of a process associated to this, while instead there exists a very strong now theory of metric measure spaces, which allows to import tools from this picture into the other picture, and hopefully state important properties of a process, for instance, just in terms of the distance, which is, I mean, something extremely desirable. For instance, the short time asymptotic of a process. Okay, so far for the form. Now let me tell you a bit about the process. Another main result is that one can characterize the process explicitly, at least for these initial conditions. So we start at a measure mu0, which is purely atomic, where we have masses Si0, and this satisfy the constraint that the measure is a probability measure. They might be finite or infinite, so capital N will be a finite or infinite number. How does the sample path of our process look like? Almost surely. Well, almost surely it has this form. The masses stay fixed, and instead the point evolve by Brownian motions. These Brownian motions are almost independent, up to the fact that they are rescaled with a volatility that corresponds to the inverse of a mass. Now let me show you a simulation for this. We start from a measure that is very concentrated, and we have atoms of large mass in red and atom of small mass in blue and purple. Now the fact that these small points jump around is in fact an effect of a simulation, of a time discretization, in the sense that they also would move by Brownian motion, but they move by Brownian motions that have a speed which is approximately 1,000 times the speed of the Brownian motions of the red dots. So basically the red dots stay still, and these points whirl around extremely fast around them, in order to satisfy the constraint that in expectation, when you take the expectation of mu t and you start your process at the Dirichlet-Ferguson measure, the invariant measure, then you would always see the volume of the base space. So basically this describes an extremely turbulent flow that in average does not move at all. Two words about the techniques. Well, this process can be explicitly characterized via quasi-homeomorphism of Dirichlet forms by translating everything into the infinite product, taking also in account the product with the simplex, which describes the masses. And this is studied in this work by Bendigoff and Soloff-Kost. And now let me conclude with an overview. So again, we start with a candidate volume measure. One needs to agree that this volume measure is the volume measure. And this is not the claim here. There are other measures that are also studied in this respect. But once we agree, then this form for this particular measure is closable, which means that we can start the theory. And the theory brings us already quite far in the sense that it tells us that there exists a process, which then we need to characterize by other means, in this case completely different means. Hopefully, when there is some good understanding of the relationship with geometries, So with Wasserstein geometry and, for instance, the Cheeger energy, one can hope to do this in larger generality. The process has this form, at least for these starting points. There's also a formal understanding of the process via the so-called Dean-Kawasaki SPD. I'm not going to go into details about the meaning of this SPD, but this is also well studied. In particular, it's studied in dimension 1 by Konarowski and von Renesse, and there's a large literature in physics about this type of equations. Finally, one can study the properties of this process. Some properties one can study directly with the Dirichlet form, all properties that are not pathwise but just old, say, in law. For instance, it is a reversible recurrent diffusion. It is not ergodic, which is something you probably would not like of a Brownian motion, but fact is it's not ergodic. Still, one can characterize completely the ergodic decomposition, so one can characterize completely the invariant sets. It satisfies what I would call a Rademacher theorem, which in particular implies that we have, say, short-time heat kernel upper estimates, so we know something about the behavior of a process for small time. Next, of course, we know that there are good starting points, which are these pure atomic measures, but it's not necessarily the case that all starting points are good starting points, so for which we can discuss explicitly how the process evolves. Of course, other than the properties, there's also a lot of open questions. There are some technical questions, but of course there's also a more important and very general one. What about other measures? There are several other candidates, for instance, the entropic measure in dimension 1, which is also being constructed in higher dimension. Say measures coming from random geometries, or measures coming from point processes. The problem is always that we need to show the closability of this form in order to start. But once we do, then the theory really brings us quite far. Okay, with this, I think I'm through, and so I would like to thank you very much for your attention.
Thank you. Is there any question?
That's a good question. This depends on the geometry, but for this geometry, no, it's not known. You should think of this measure as, or at least the way I think of this measure is coming from statistical mechanics. The Dirichlet-Ferguson measure is, in a sense, as close as possible to being a Poisson measure, but you have the constraint that you want to be a probability measure. Poisson measure is not probability, so there is a trade-off, but this is the closest that you can get. So for instance, this identity, if you're familiar with the Mackey identity for the Poisson measure, this is the replacement of the Mackey identity, which means that if your, say, differential operator is the gradient corresponding to this convex combination, then you can expect several functional inequalities, for instance, say Poincaré, Lotz, Sobolev, and so on. For the Wasserstein geometry, which is completely different, this is completely open.
Please.
This is also a very good question. In principle, if your weight is sufficiently regular, then this will go through in the exact same way, because the construction does not really depend on any properties of M. So the idea is that there must be a relationship between M and the Laplacian on the base manifold in order for you to do the construction and characterize the process. But if you take the corresponding weighted Laplacian, then everything will go through as it is here. Yeah. That's true. In this respect, certainly in this case, one would need to consider each, say, slice in the ergodic decomposition, for sure. Of course, there's also hope to do this for other measures, but also for other measures there are negative results. For instance, for the entropic measure in dimension 1, it is known that this does not satisfy the curvature dimension condition. So again, of course, the lack of ergodicity is a good indication that you cannot expect functional inequalities in very general terms, but at least for each invariant set, there is still some hope to do it.
So a couple of questions. So one is whether if you take a random point at a random measure, this behaves like M, and the other one is so it seems that something like so the random measure that PM takes is like you know, a sum of Dirac masses. Maybe they are independent with some weights that are something, so you can say something like that. You expect something like that, at least, I don't know, the torus or something like that.
So if I understood correctly what you said, and in fact this is true in general, so the distribution of the atoms is that they are independent and distributed according to M. And the important part is the distribution of the masses. They are distributed as the so-called Poisson-Dirichlet distribution on an infinite dimensional simplex. So exactly as you hinted, when you take the expectation of your random measure, then you would get precisely M. This is why this property preserves also along the flow, which means that indeed the flow is really extremely turbulent, but in average is constant if you start from a invariant measure. And it's constant being the volume of the base space. Point is that when you start the evolution, you quickly see this is not a stochastic flow, because points that are very small move extremely fast, and this breaks any type of continuity of the evolution of the points. So even if at fixed time slices you are very nice, indeed you are the volume in expectation, then still when you start the flow of time, complicated things can happen.
Okay, I think we can close here the session, and thanks again. So we resume for the afternoon session in the same room at 2:30.
So welcome to this afternoon session. The first speaker is Guillaume Carlier from Paris-Dauphine. Guillaume, thank you very much for starting.
Thank you very much, Giuseppe. So it's a great pleasure to be here, to be back in Pisa. I was missing it. I'd like to thank the organizers for this wonderful event. We waited for too long, actually. And so today I'm going to present a recent joint work with Luca Tamanini and Paul Pegon, both are in the audience, about a convergence rate result for entropic optimal transport. So the setting will be the following. I will work on RD. Okay, with start from an optimal transport problem with the first C, which will be at least continuous most of the time, or then C11. Compactly supported marginal mu plus and mu minus, and as you know, it's very popular in Lucas field. Oh, but can you hear me or? Ah, okay. And then? Okay, so let me denote, I have a small parameter epsilon, and in addition to the transport cost, I'm going to add the entropy times epsilon of the plan with respect to the product of the marginals, so that the independent coupling, the product of the marginals, make this cost finite. And I'm going to minimize this among transport plans between mu minus and mu plus. So of course, when epsilon goes to 0, you recover the Monge-Kantorovich problem. And the question I will ask is how fast this value converges to the value of the Monge-Kantorovich problem. Right? So when you, so of course, entropic optimal transport, as I said before, has received a lot of attention in the last decade because of its use in numerical optimal transport, the famous Sinkhorn algorithm. So Marco Couturi is quite responsible for that, the success of his story. And there's another story which goes back to Schrödinger in the 30s, which links this kind of problem to the so-called Schrödinger bridge problem that in particular. Okay, sorry. promise I will not move too much. Another story which is related to this is the so-called Schrödinger bridge problem, which in particular was made quite popular with the work of Christian Leonard, who in particular proved nice gamma convergence results. So in particular, it's well known that under quite general circumstances, the value of the entropic transport problem, V epsilon, is converging to the value of the corresponding Monch-Kortewicz problem. But the question is how fast? And when you think a little bit about it, there cannot be a universal answer. It depends. It has to depend very much on the assumption, the kind of assumption you make on C and on the marginal. So, for instance, for finitely supported marginals, mu plus and mu minus, this is entropic approximation of linear programming, and it has been studied in depth in a very nice paper as early as in the 90s by Roberto Cominetti and Jaime San Martin, who proved not only precise expansion in epsilon, but also nice exponential convergence results for what you can think of as being the potential. Another quite strong example is if you think there's no optimization. For instance, the C of xy is a function of x plus a function of y. Of course, there's no optimization. Right? The transport cost is constant. So in this case, the epsilon is constant. So it's the best kind of convergence you can have. So to look for a regime of convergence, to look for convergence rate, for sure you need to assume something about the non-degeneracy of the cost, something like this. Okay. So it's been very much studied also, this question of speed of convergence in certain context. It's fair to quote a very nice paper about 10 years ago by Adams, Dirichlet, and Zimmer. It was not. It was related to large deviation, point of view, not exactly to entropic optimal transport. And more recently, Sumikpal and others studied the expansion of the epsilon up to a term in epsilon, but under quite strong regularity conditions on the transport. So we assume that there is a transport map and that it is Lipschitz typically, this kind of thing. There are also very nice recent results, which still, again, for the quadratic cost, which rely on the dynamic formulation of both Monch-Kortewicz, the Benhamou-Brenier formula, and the dynamic formulation of the Schrödinger bridge problem, which enable, for instance, Giovanni Conforti and Luca Tamanini to go up to the term in epsilon square. Okay, and there's also slightly more recent work by Gabriel Perret, Viala, Léger, and Shiza with similar results. I don't want to spoil Luca, but he's going to talk later this afternoon about convergence result for the gradients of the potentials. But all these results, I would say, rely on quite specific assumptions, either the regularity of a transport map or take advantage of a dynamic formulation. But for a generic cost, you cannot really take this for granted. So what I would like to present is ideas which lead to the following results, which we obtained with Paul and Luca. We say that typically the expansion just identifies the first term if the marginals have bounded densities, and if the cost is C2 and non-degenerated. By this, I mean it was a condition that was identified in the paper that influenced us very much by Robert McCann, Brendan Pass, and Mikawaran. The condition is to avoid the case where there is no optimization, the cost is constant, and the good condition is that the matrix of mixed partial is everywhere non-singular. Okay, so we call it in this paper infinitely twisted, but it's a non-degenerate condition. So under this condition, you can prove that the V epsilon, the value of the EOT with parameter epsilon, is the value of Monch-Kortewicz plus dimension divided by 2 epsilon log of 1 over epsilon, and the remainder is big O of epsilon. Okay. I'd like to mention also that we are in a regime here. Just this assumption does not guarantee even that there exists an optimal transport map. Okay, and not even that there is uniqueness of the optimal transfer plan. So there are examples in the paper by Robert, Brendan Pass, and Mika Rowe. So here is and the corollary is that since the term in epsilon log of epsilon is minus dimension divided by 2, it does not depend on the marginal at all. If you kind of look at the variant of entropic optimal transport, which is called sim-core divergence, when you subtract the value of the EOT between mu minus and mu plus, let's say the mean of the value of the entropic cost between the first marginal in itself and the second marginal in itself, the term in epsilon log epsilon disappears, and in fact the error should be big O of epsilon. So in the remainder of the talk, I'd like to give some details about how you prove this, and in fact there are two kind of different results to prove that this is in some sense sharp. I will prove an upper bound, saying that the lim sup of this ratio is less than dimension over 2, okay? At least for C11 costs. And for this, basically, the proof will use a certain approximation I will describe, called block approximation, and a certain variant of Alexandrov theorem. And using the dual formulation of those problems, we get a similar lower bound. So the limit of this ratio is bounded from below by dimension divided by 2. And here, the arguments are a bit different. They are based on a quadratic detachment bound, which is somehow reminiscent of Milti's trick, which I would like to detail in this talk, and which is of course linked to the seminal work of Alberti and Ambrosio on fine properties of monotone maps, and which plays also a role in a nice result of Robert and his co-authors about the de-retractability of optimal plans if the cost is non-degenerate. Okay. Yeah, exactly. But I'll be more precise. Yeah, exactly. So you see, you need some smoothness in some sense for the bound from above, and from below you need some degeneracy of the certain gap function. Okay. Yep. You mean a priori or? No, you will see, but in fact it just depends on this condition, right? You will see there's a lemma which tells you that a certain duality gap will be quadratic in D coordinates, and that's what is important to get the D over 2. That's the only thing that plays a role. Precise other properties of C are not so important. Of course, if I wanted to say more, to go to the term epsilon or epsilon squared, I probably need more specific, to be more specific. Okay. Okay, so first of all, I'd like to say a few folklore things about the dependence of the epsilon with respect to epsilon. Then I give some details about the upper bounds, and also about the lower bound. Okay. So, okay, it's basically same problem that we written here, and of course it is a strictly convex problem, so you have a unique solution. But you see, you're adding a quite nice strictly convex term, which make the unique solution gamma epsilon quite rigid. In fact, it has a special property. Basically, the Euler-Lagrange equation for this minimization problem tells you that the log of gamma, well, gamma is a density with respect to the product measure, whose log should be given by some potentials, like control H potentials, which plays the role of Lagrange multipliers for the marginal constraints. So in fact, gamma epsilon should have this form, this exponential form, okay, for two potentials phi and psi, which are essentially unique in some sense, of adding a constant to one potential and subtracting it to the other. And the fact that this is a plan between mu minus and mu plus leads to a system between phi and psi, which is a system of nonlinear integral equation, which says that phi is given as a function of psi by this formula, okay, and psi satisfy. So it's a sort of soft C transform, if you want. Okay. So what is known is that, and this is at the synchron algorithm is, roughly speaking, iterate these two equations and hope to converge to a fixed point, which is known under various conditions. And well, so it is quite well known that these potentials exist. They can be chosen continuous because the cost is continuous, and there are various proofs. I quote one, which is personally my favorite one, is the one by Simone and Augusto Girolin. It's just by using synchron as the iterates of this map. And okay, so in terms of the value, what can be shown? I'm not going to give the proof, but it's a sort of inverse function theorem. When you look at the linearized system, it's quite nice. It has nice invertibility property. And from this, you can deduce that, so first of all, the epsilon is continuous for positive epsilon. It's obviously non-decreasing because you add an entropy, which is non-negative. It's obviously concave because it's an infimum of an affine quantity of epsilon, but it is also super smooth. For strictly positive epsilon, it is even analytic. It's a remark, I don't know what to do with this remark, but it suggests that you should be able to solve the Schrödinger system I showed before, even for some complex values of epsilon. Okay, it's just a fancy, I think fancy remark. I don't have a precise application in mind, but I wanted to mention this. But of course, if you are in the regime, let me show again the definition. If there exists an optimal transport plan, which is a finite entropy with respect to mu minus times mu plus, you know that the error would be in epsilon. But in general, you cannot expect that. In general, optimal transport plans are sparse, and they have an infinite entropy with respect to the product measure. So, in general, you cannot expect a big O of epsilon term, and the guess is that it should be in epsilon over epsilon, but to identify the good constant is something I would like to explain now. Other question at this point? Okay, so let me give a first upper bound in the case of a Lipschitz cost. So you have your two measures. You assume that the cost is Lipschitz, and the marginals are compactly supported, and you can define an entropic notion of dimension of a measure, which goes back to Reni, which is given as follows. So you give yourself a scale, delta, a small delta positive, and you look at partitions of RD by some sets AN, each of diameter less than delta, and you look at the optimal partition with respect to this entropic-like term. Okay, so the upper entropic dimension of the measure is the lim sup of h delta of mu divided by log of 1 of delta as delta goes to 0. Okay. So the first proposition is that you can bound from above the entropic cost by the transport cost times epsilon, the minimum of what we saw in the definition of Reni's dimension, the minimum of h epsilon between the two measures, plus the Lipschitz constant of the cost times epsilon. So in particular, since this guy is bounded by the Reni's dimension time log of 1 over epsilon, you have this bound. Okay, you can bound the error is bounded by the minimum of the entropic dimensions of the two marginals. Okay, which in terms are bounded by dimension, of course, by the ambient dimension d. So the proof goes like this, not super complicated. It's based on, of course, the deal. What you have to do is to approximate the optimal, unoptimal transport plan, which is typically sparse, by something which has a finite entropy. So first of all, you give yourself a certain scale delta, and you look for a partition of RD by sets AN with diameter less than delta, and for such sets, you look at the ANs which have positive mass, And what you do on such cell, you're going to glue some independent couplings in this way. So you look at these measures on the good cells AN, those are seen by the measures, and you weight the product measure by gamma naught. So I forgot to say, gamma naught is an optimal transfer plan. Okay? And when you glue everything together, so when you sum over all sets in the partition, you got a transport plan, gamma delta, which has some nice properties. So first of all, in W infinity distance, it is delta close to gamma naught. So and so when you use this gamma delta as a competitor in the entropic optimal transport problem, what you get is that the epsilon is less than the integral of C d gamma delta plus epsilon times the entropy of this guy. Okay? And since gamma delta is delta close to the optimal plan gamma naught, the error you make is just the Lipschitz constant of C times delta. So now you have to control this term. But this term, you can bound it from below by the sum of the mu plus aj log of 1 of mu plus of aj. But when you try to look for a partition which minimizes this quantity, this is the quantity you get in the definition of the Riemannian dimension. So in fact, if you minimize with respect to the partition aj, what you get is that the error in entropy is bounded roughly in a terms which is the Riemannian dimension of 1 marginal. I put mu plus, but there is similar mu plus and mu minus play symmetric roles. So the error is log of 1 over delta times this Riemannian dimension. So of course, if you choose epsilon, if you choose delta over the epsilon, you get this one. It is not exactly what I announced in the beginning, because in the beginning, I did not have d, but I had d divided by 2. But for this, I need more assumptions on C. So the assumption I'm going to make on C now, it is C11. Okay. I forgot to say that just for Lipschitz cost, the upper bound which is here is sharp. You can just with a cost which is the distance, even in 1D, you can do an explicit computation. So you see that dimensions epsilon log over 1 over epsilon is the right order of the error. Now what you can do, of course, is instead of looking at the cost, you can subtract some potentials, some Kontorovich potentials. Okay. So if you do so, you see that since gamma delta, the block approximation, and gamma naught, the optimal plan, unoptimal plan, since they have the same marginal, the integral of C d gamma delta minus gamma naught is the same as the integral of the gap. So the gap is just the cost minus the Kontorovich potentials. But now what is good with the Kontorovich potentials is that they are such that the gap not only vanishes on the support of gamma naught, but it's also minimal. So if the gap was smooth, okay, let's say C11, the error would not be of order delta, but would be of order delta square. But of course, it's not true, because the Kontorovich potentials, the best you can hope is that they are semi-concave, so that E is a semi-convex function. So it's not, you hope you gain an order of magnitude, but you have to work a little bit. And that's what is done here. It is what the mention, the variant of Alexandrov theorem I mentioned in the beginning, that if you have a semi-convex function, so you have to add a certain quadratic function to make it convex, then in fact you have a certain integral, a certain integrated version of the difference between the function and its first order approximation, which behaves in R squared. So R is the radius of the bool. So I take the soup over points y's, which are R closed to X. Okay. So when you combine this refined Alexandrov result with this basic estimate you get using Kontorovich potentials, you get exactly the d over 2 epsilon log over 1 over epsilon error I mentioned. Okay. Okay, so what about lower bound? For lower bound, it's of course it's quite natural to use dual formulations of V epsilon and V naught, where you write the minimal value as supremum over potential. So entropic optimal transport is well known to be, the supremum can be written as a supremum of this quantity here among potentials phi and psi. So of course here, again, I'm going to use as test functions, as competitors, the Kotorovich potentials, okay? So by Kotorovich duality, the integral of phi d mu minus plus psi d mu plus is precisely the optimal transport cost. And then comes this sort of error term, which is written in a log Laplace form, where E is again the detachment, the duality gap. So it's the cost minus phi plus psi, something which vanishes on the support of gamma naught, but which is non-negative everywhere. Okay. So we'd like now to have a lower bound on this function E, which is C minus phi plus psi. So that's where the non-degeneracy condition comes into play. And I'd like to explain the idea. It's really easy to follow in the case of the quadratic cost. It works also in the non-quadratic cost and with this condition of non-degeneracy on this matrix. But in the quadratic case, I'd like to give some details because it's quite, and I think it's quite funny. So you have the quadratic cost, okay? So the Kotorovich potentials are phi and psi, but you know that up to, you can look, instead of the Kotorovich potential, you can look at the Brogniar's potentials. So this is the squared norm divided by 2 minus the Kotorovich potentials. So these are Fenchel conjugate, Legendre conjugate potentials. And the gap is the same as the gap in Fenchel-Young inequality. So it's f of x plus s star of y minus xy. Okay? So what we know is that it's something which is everywhere non-negative and which vanishes precisely when y is a subgradient of f at x. Okay? And now comes the Mintis trick, saying that y is in the subgradient of f at x. You can add x on both sides of this inclusion. But here, on the right-hand side, you got identity plus a subgradient, so it's invertible with a Lipschitz inverse. So you can write what was an inclusion, a subdifferential inclusion, as an equality. So you can write, you change coordinates if you want, you express, instead of being in the space xy, you express x as a function of x plus y using the resolvent which is here. Okay? So Young's inequality tells you that E is non-negative, and the zero set is when x is linked to x plus y by this formula. But in fact, there's a quantitative version of this, which says that the gap is larger than the squared error between these two gaps. Okay? And the proof, I want to present the proof, it's super simple. It's two-line proof. So the trick is you add two extra points, x prime and y prime, which we choose later on. So by Young inequality, you see that f of x, you can use y prime as a possible slope, so it's larger than this guy, and f star of y can be, you use Young's inequality again to bound it from below by this guy. So now you sum to get the gap, and you have to subtract scalar products. So summing this inequality, what you get is that the duality gap, the gap in Fenchel-Young, is bounded from above by minus the gap at x prime, y prime, plus the scalar product. So the best thing to do is to make this guy, with the minus sign, is non-positive, to make it 0. So to make it 0, you are going to choose, first of all, you're going to choose x prime and y prime such that x prime plus y prime is x plus y. So if you do so, you see that, and then, sorry, I forgot to say this. So first of all, I'm going to fix x prime and y prime so that they have the same sum as x plus y. And of course, I want the gap to vanish. So I'm going to choose x prime to be the resolvent computed at x plus y. If I do this, the first term cancels. And what you get is that x minus y, x prime and y prime minus y are collinear. So x minus y, x prime, this scalar product is just the square norm of x minus x prime, which is this guy. Okay? So there is a quadratic detachment bound for the gap, which, well, maybe I should be, which can be used. It's a cheap way, and it's a cheap way to somehow, in some situations, to look for some stability of optimal transport. Okay, we know that the optimal plan is supported by the graph of the differential of a convex function. You could ask yourself, okay, if I'm not optimal, but if I'm optimal up to a delta, if I'm a transport plan between mu plus and mu minus, which is optimal up to some delta, am I, in some sense, in some quantitative sense, concentrated close to a set which is close to the subgradient? So this is typically, you can use this inequality I showed you to prove this, right? So you see, this is something which vanishes exactly when gamma is concentrated on the graph of du. I don't know why it is u and not f. Sorry about that. I changed my notation. And in particular, you can use this for the epsilon, for the entropic optimal plan, because we saw in the previous part that the error is at worst d epsilon log of 1 over epsilon. So in some sense, the entropic plan should satisfy this. So in some L2 sense, it should not be too far from the entropic, from the graph of the subgradient of a convex function. Okay, so now let me come back to the purpose of the talk, which was to lower bound the gap. So in the quadratic case, we have seen that if you make the change of variable, instead of xy, you look at x and x plus y. We have seen, because of this the lemma we saw before, we know that in d dimension, d independent dimension, E should behave like a square. So then it says that this Laplace transform should be epsilon to the minus d over 2, and then the error should be lower bounded by minus d over 2 epsilon log epsilon. Okay. This is where the lower bound comes from. Now, if we want to use more general costs, we have to be a little bit more precise and to argue, as in the paper by Robert, Brandon Pass, and Mika Warren. And okay, you have so the assumption is that C is of class C2, it is non-degenerate. Sigma is the zero set, the minimal set of the gap. So the gap is C minus phi minus psi, where phi and psi are Dondrovich potentials. So now you introduce this quantity, so you give yourself a certain radius r, and you maximize this operator norm, this distance to the identity map when x prime and x are a distance less than r, so it's something which is small when r is small. And using this quantity, what you get is exactly the analog of the previous lemma, but for more general costs. You remember we had the gap at a point plus the gap at another point was bounded by a quadratic quantity. So the quadratic quantity, so here, think that you are around a certain point x bar, okay? And you have 2 points x and x prime, which are in the ball, center x bar and radius r. And you can bound the gap by this quadratic quantity. Well, you have changed coordinates, okay? It's Minty's trick again. So instead of the coordinates x, y, so I forgot to say that, okay, x bar is already a couple, right? It's a pair x, y. So you got x and x prime are couples, right? They live in the product space. So sorry about the notation. but it's a bold X. So think that bold X is a couple. Okay, and now we can use this detachment, quadratic detachment estimates. Of course, it's interesting when delta V is 0, so x and x prime has the same V coordinate. Okay, and also when the gap vanishes at the point x, which is the case on the support of the optimal plan. Yeah. Okay. No, but okay, sorry. It's delta U, delta V are new coordinates, right? So you can. So bold x, both x primes are couples, and delta U, delta V are new coordinates for the couple in the product space as well. Am I clear? And you see this from the formula. So bold x is xy. So you twist this guy by this map. You twist the other guy with the minus sign. So you see, this is just the direction in which so it's delta U. Sorry, UV is a new chart, but in the product space. Okay. And then you combine everything, right? Duality, these coordinates. You have to play a bit locally, and it's the same thing, right? The gap will be quadratic in d dimension in the 2D dimensional space. So for the same reasons, you will have this support. Okay, and I think that's all I wanted to say up to this point. I'll be happy to answer questions. Okay. Thank you so much.
Thank you. We have plenty of time for questions.
Hi. So you mentioned before that there are results for the discrete case, which are much older. Do you recover them? Do you improve upon them?
No, not at all. It's a totally different regime.
Yes, I mean.
It's really, you compare somehow. No, you really compare the bounds with Gaussian bounds, right?
Yes.
It's really something you cannot do in the discrete case.
So you don't have also
the
mixed case, so if one is discrete and the other one is continuous, for example, do you have something to say about that?
It's difficult to say because all the constants which appear in the work of San Martin and community depends a lot on the geometry of the simplex, the dimension, the size of the facets, and so on. It's not something which is easy to pass through. I forgot probably also to mention that there are semi-discrete results also from continuous to discrete. All this as a special. So I wouldn't say it's a different, really a different regime. But thanks for asking.
Hi. Thanks a lot. It's very interactive. So these. So first question is. Can you extend this also to the Monge case? Because maybe it's so.
Okay, for the Monge case, you meant for the distance, right?
Yes, with the distance.
For the distance, we know that the constant is d, not d over 2, and it's sharp. The R is in d epsilon 1 over epsilon.
But it's not so. In that case, you have only one inequality. You don't have the other.
Yes, but you can do. Yeah, but. Yeah, but you can prove that this bound is sharp, for instance, if you have the uniform measure on an interval and the uniform measure on another interval in 1D, then you compute and you see that the error is the constant in front of this is really the dimension.
And then the other question is the inequality that you showed, the skew. So when you do the change of coordinates, it is similar to the change of coordinates that I think they do Léger. At least I follow the seminar. There is no paper, I think, but they do the coordinates which are the orthogonal ones on the map, similar.
Yeah, that's right. But this is not exactly what we do, right? We take a point in, that's right, the same quantities appear. The regime is not the same. They go further because they identify higher order terms. They go further in expansions, but they assume a lot of regularity on potential and so on, which we cannot take for granted here. And we cannot assume also that uniqueness of the gamma naught, or the fact that it has a graphical structure and so on. So what we do here in the change of variables, we kind of freeze a point, x bar, in the zero set of the gap. And then we kind of linearize around this point and recover by finitely many charts the whole support this way. So in the spirit, it looks the same, but this is gluing linear change of coordinates together. Whether what they do, I think, is more global and more non-linear. If I'm not mistaken, the philosophy is...
Yeah, so it's interesting to me because yours is implicit, if you want. Theirs is explicit change of variables, so they need the map, and you are doing the implicit, so you don't need the map. So
no, I don't need the map. That's the point.
You know, so
yeah.
Are other questions? Not. Let's thank Guillaume again. We move to the next talk. Okay, so the second speaker of this afternoon is Max Fathi. He will speak about globally Lipschitz non-optimal maps. Thank you.
Thank you very much, and thank you very much for the invitation. So I'm particularly happy to speak about these results here because I started working on this at the 2016 edition of this conference. Maria Colombo gave a talk about some related results that have kind of inspired me ever since. So, and I also should say, I'm saying non-optimal transport map not as a provocation. It's because I don't know how to prove these things for optimal maps. So it's joint work with Dan Mikulinser and Yair Schenfeld. And the basic question we were wondering about is, okay, you have the Brognier map from two measures, and let's, to fix ideas, take the starting measure to be the standard Gaussian measure. Everyone, can you read if I write at the side? Thanks. Okay, and we transport it onto another measure, which is a perturbation of the Gaussian measure, or something else really. But let's start with Gaussian onto something that has a nice density with respect to a Gaussian. And we look at the Brognier map. And the question is, when is the Brognier map Lipschitz globally? And of course, we have local regularity theories. What I'm interested here is really in two things that are maybe not entirely classical in PDs, but very relevant for applications in probability, is that we want, well, global estimates, of course, is very classical, but, and we want, in particular, to know whether getting dimension-free estimates on the norm. And an answer in a particular setting is a theorem of Caffarelli, which states the following. If f is concave, T, still the Brognier map, so optimal transport, quadratic cost, is 1 Lipschitz. No matter what the dimension is. So, and this 1 Lipschitz bound is of course sharp, because if you transport the Gaussian onto the Gaussian, you have the identity. So, okay, so this gives a conclusive answer in the particular setting of measures which are more log concave than the standard Gaussian measure. And this has many applications. It contains, I will not speak too much about the applications in probability, but it contains many results of interest in probability and statistics. It implies Gaussian isoperimetric inequalities. It implies kind of all the conclusions of Bacry-Lemery type theory in the Euclidean setting. And then natural question is, okay, so we have a very nice theorem, a nice class of examples. What more can be done? Are there other settings where we can prove an explicit bound on the Lipschitz norm of the optimal transport map? And at this point, I think the furthest answer I am aware of is the theorem of Colombo, Figali, and Javeri. Was published in 2017, which says that so if the Hessian of f is bounded from above by some constant, and the support of f up to a constant, by which we mean it's not zero outside a compact set, it's constant outside a compact set, is included in some ball of radius r. Then t is some constant that depends on lambda and on r Lipschitz. It's not written explicitly in the paper, but in principle it can be made explicit, and it is exponentially large in r squared. So that's at this point, that's, as far as I'm aware of, that's the end of the story for now for optimal transport maps. But we were wondering what can be done beyond this. Are there other examples? And one way of trying to look for inspiration and if there are other assumptions that could work is to try to simplify the problem. So one way of simplifying this is to take the Monge-Ampère PD for the optimal transport map, and instead of directly looking at estimates for the solution, linearize the PD and look for estimates for the linearized PDs. So if we were to write the Monge-Ampère equation for the Gaussian, what do we get? We get exponential of minus x squared over 2, let's forget about the constants, is equal to exponential of f of, okay, t is the gradient of a convex function, f of grad phi minus right phi squared over 2, determinant function of phi up to a constant. And now we can take the log of the Monge-Ampère equation, linearize, and what do we get? So if f, we replace it by some epsilon f, so a small perturbation, and we look for a solution of the form x plus epsilon gradient of h. The PD becomes Laplacian of h minus x dot grad h equals f minus average of f with respect to the Gaussian. Okay, the constant probably looks a bit weird, is that I cheated a bit by doing this replacement, is that we need probability measures on both sides, so we have to add a constant here to ensure the mass to be 1. Okay, so that's the PD that comes up. And to say that the transport map is Lipschitz, we would like to have a bound on the Hessian of h. So what can we say about the Hessian of h? Well, we have a very convenient property for this PD is that we can write down the solutions. So the solution, there is a, well, they're not unique, but there is a nice solution to this PD, which is the following. H of x is equal to the average from 0 to infinity, integral, of, you take f, you apply it to e to the power minus tx, you add a second variable y multiplied with square root of 1 minus e to the power minus 2t. You average with respect to the Gaussian in y, and then you integrate from 0 to infinity. And this, you can check that using an integration by parts, that this is actually gives you a solution to this PD. Sorry, I forgot to remove the average. It's f minus its average to which we integrate. Okay, so from this explicit formula, you can try to figure out what's going on. And now, okay, as a test point, you can think of can we already see at the linearized level Caffarelli's theorem? And the answer is yes. Caffarelli's theorem corresponds to the case f is concave, sorry. So if f is concave, well, taking your average with respect to the Gaussian, in x this is still a concave function. Then you take an integral, you still have a concave function. You add in the minus. Sorry, it seems like I got some. Wondering if I got their sign wrong somewhere. Want to show that. Probably I got the sign wrong here. I realized, sorry. So you take f concave. What you get is that the solution H is convex, and indeed you get a map that is essentially Lipschitz for epsilon small. So this is kind of like it doesn't prove Caffarelli's theorem. It kind of predicts at the linearized level that you should expect something like that. But this is not the only case where we know things about the Hessian of H. And another example is if f is L Lipschitz, then it is known. You can prove this on the explicit formula, that it implies that the Hessian of H in the Hilbert-Schmidt norm is bounded by L, same constant. So we have the gain in regularity, and this suggests that maybe if we look at the Lipschitz perturbation of the Gaussian, the optimal transport map from the Gaussian onto it could be globally Lipschitz. And I don't know how to prove this. So that was what we were trying to prove, and we don't know how to prove. So what we did instead is the following theorem. There is another map. In this same assumption, so Gaussian onto Lipschitz perturbation of the Gaussian. That's exponential of some numerical constant that's explicit times the maximum between L and L squared Lipschitz. So something that is exponentially large in the Lipschitz constant of your perturbation, but it's still Lipschitz. And this exponential behavior is sharp because with Lipschitz perturbation, you can deform your Gaussian into some double well potential with height L over some size L. And it is possible to show by hand that by proving Poincaré inequalities for these kind of two double well measures, that the Poincaré constant has to be an exponential of L squared when L is large. And one can show that the Lipschitz norm of a transport map cannot beat the Poincaré constant. So okay, so that's the theorem. I hope to roughly give you the ideas how to prove, and then I will discuss how it works beyond the Gaussian setting, because the proof I will describe is not particularly Gaussian in nature. This height is okay. Yeah. So okay, yeah. So roughly speaking, imagine you have a C Lipschitz map from the Gaussian onto another measure. So T sends you Gaussian onto mu, which is C Lipschitz. Then the variance under mu of some test function, let's call it G, is the variance under the Gaussian of G composed with T, right? And then you apply the Gaussian Poincaré inequality to this measure. So the Gaussian Poincaré inequality tells you that you can bound the variance of a function by the L2 norm of its gradient. So what you get is that this is smaller than gradient of g composed with t squared d gamma. And then, if you apply the fact that t is C Lipschitz, what do you get? You get that this is less than c squared average of grad g composed with t squared d gamma. And then you pull it back. This is c squared average of grad g squared with respect to mu. So Lipschitz map implies Poincaré inequality, and you deform the Poincaré constant by the square root of the Lipschitz norm. Okay, so that's sorry, where was I? Okay, so now I will explain the construction of the transports. And the construction is due to its, what we now tend to call a Langevin transport map. And the construction is due to Jung-Gun Kim and Emmanuel Milman in 2012. It goes the following. So the first observation is when we linearize the PDE, what we got was the operator Laplacian minus x dot grad. And this operator is the generator of the Ornstein-Uhlenbeck process. So it's the generator of the stochastic process, dxt, equal minus xt dt, plus Brownian noise. And this is a very nice stochastic process. It's ergodic. As the time goes to infinity, the law of such a process, started from any initial data, is going to converge to a Gaussian distribution. So by starting x0 with density EF gamma, then I'm writing x infinity. This is not a real limit, but just to say that, well, the law of xt is going to converge to the Gaussian. So this process generates an interpolation between your measure and the Gaussian measure. And now the evolution xt has a law of the form rho t gamma, and the evolution of the density is according to a PDE. dt of rho t gamma is equal to the divergence of grad rho t times gamma. This is the PDE. Now we can rewrite this as divergence of gradient of log rho t times rho t gamma. I'm just rewriting things. Now, if I think of this as a vector field, let's call it Vt. The marker is dying. Okay, sorry. Hopefully. Okay, so let's call this Vt. And now let's pretend that this vector field has nothing to do with rho t, right? Then now this PDE is also gives you the evolution for the flow of the following ordinary differential equation, just x dot t equal minus Vt of x2. So if you start this deterministic ODE from initial data x0, then the law at any time is going to be the same as the law at the same time of this process. The trajectories have nothing to do with each other. This is random, homogeneous in time. This is non-random and homogeneous in time. But the measures are the same. So now we have an interpolation between our two measures that is given by the flow of an ODE. So how can you construct a transport map here? Well, just follow your ODE to construct a transport. And then, so Tt of x, no, let me call it differently because it's not a transport map, gives you some is the solution to the flow, and it's going to generate a transport in time t from our distribution at initial time onto the law of xt. So now I would like to, what do we want? We want a Lipschitz map, but not in this direction, in the other direction, and for t goes to, at infinity. And now, at what condition is the inverse of a map Lipschitz? So you want points not to get too far apart. It means that the inverse map should spread points apart. Well, to show that points are spread apart, you just look at two solutions with different initial data. You differentiate in time, and you want a Grunwald type estimate, and it turns out that if the gradient of Vt with this sign convention is bounded from above by some lambda t, you get that the Grunwald estimate, this is greater than minus 2 lambda t xt minus yt squared. So that the map, the inverse map of st, is going to be exponential of the integral of 0 to t of lambda s ds Lipschitz. That's it. So now you want to get t goes to infinity, and we have a condition to have a Lipschitz transport map between our two measures. All we need is to show regularity properties on the solution to this PD. Really, we want to say something about the gradient of Vt, so about the Hessian of a solution to the PD. Now we started with initial data, so maybe the first thing I should say is that this recovers Caffarelli's theorem for the following reason. It is a theorem that if you start with initial data that is log concave with respect to the Gaussian, so the explicit representation I alluded to, so there is an explicit representation of the law time t as a convolution between your initial data and a Gaussian, and it happens that convolution preserves log concavity. So actually, if lambda 0 is less than 0, this implies that lambda t is less than 0 for any t, and then you get a one Lipschitz map. But now here we started with initial data that is log Lipschitz. So at time 0, nothing. We don't have an estimate at initial time. But we have regularizing properties of the flow. This is a very nice parabolic PD. And the regularity properties we have are of the form Hessian of, how did I call it? So if we write, let me write it in semigroup notation. So so here PT is going to be the semigroup associated with the PD. Then what we have is that the Hessian of PTF is less than something that for short time is like 1 over square root of t. We gain a derivative in 1 over square root of t. For a long time, the process is nicely ergodic. And so it's going to be something like gradients of log f. So let's say gradient of log f times PTF. So we do have regularization. So for the Ornstein-Uhlenbeck semigroup, we have an explicit formula. This can be computed. Now then to prove the theorem I stated earlier about getting a Lipschitz map, all you need to do is plug in the fact that you know at initial time, I shouldn't have called this f, sorry. Which row? Grad log row. The log of the initial data was Lipschitz. We plug in the bound. We get something that's like e to the power minus t over square root of t. It's integral in time from 0 to infinity. and the constant that comes out is exactly what you want. Sorry, and I forgot, this is a squared here, actually. It's an L squared. Okay. Now, if you look at the proof, the Gaussian nature is, so I alluded to, I mentioned this explicit formula that allows you to do computation, but beyond this the fact that computations are easier, the ingredients are not particularly Gaussian. What matters is that you can prove a regularity estimate along a flow in the following way. So how to do this in a non-Gaussian setting? Then let's say you have another measure with some density e to the power minus h, and you wanted to transport it onto exponential of f minus h. I will still think of f as Lipschitz. Now h is something else. Now the natural counterpart to the Ornstein-Uhlenbeck flow is the following STE. dxt equal minus gradient h of xt dt plus square root of 2 dbt. You still have a PD for your, so the generator of this stochastic differential equation is L equals Laplacian minus grad h dot grad. In the Gaussian setting, h is x squared over 2, we get the x. And the question becomes, what can we prove so far as regularity properties for this flow? And if you can prove regularization properties that are integrable in time, you're done, you have a Lipschitz transport map. And now the theorem. So assume that I claim no sharpness for the assumptions I make on h. These are just one setting where we can prove things, among others. Assume that the Hessian of h is bounded from below by some strictly positive kappa. And assume that the third derivatives are bounded. So the gradient of second derivative in any direction of h is less than some beta. This beta is equal to 0 for the Gaussian. Then what you get is, and still the initial data that is f is L Lipschitz, then you get a map that is exponential of some constants, some explicit numerical constant, L squared over kappa plus L over square root of kappa plus some L beta over kappa squared. Lipschitz map. Okay. So now I have to make a confession, is that the proof of these regularity estimates is we did it. Well, we mostly recycled results of other people, and that there is a vast literature for proving such estimates using Malevin calculus and the Bismuth formula. So there are stochastic representations of the PD. And on these stochastic representations, it's possible to do explicit computations and get bounds. They're not as nice as in the Gaussian setting. It's not just an integral. The representations are not local in time. They depend on the whole trajectory of your stochastic differential equation, but you can work with them. I don't know how to prove these such explicit regularity estimates in the PD setting, and actually, even in the linearized regime. So, okay. I should mention some open problems. This is something that bothers me quite a bit. So if you look at Laplacian of h minus grad large h dot grad h equals f with f1 Lipschitz, and Hessian of h greater than some kappa, strictly positive. The Hessian of h, an operator norm, is bounded by some constant that depends on just on kappa. I don't know of any PD proof of this result. Like all the proofs I know of are probabilistic in nature. So is there a PD proof? I would love to see something like that. The two difficulties compared to classical regularity estimates for elliptic problems are that the bound is global in space. We're not working on a compact set. And it's dimension free. But yeah, so okay. How much time do I have left? A bit of time. So maybe I should say a few words about how, not the full proof, but how these probabilistic regularity estimates work. Roughly speaking, what we want, we have the following representation. The semi-group, you can think of it as if you have your SDE, ext equal minus grad h of xt dt plus the noise. This PTF I wrote earlier, so we'll call it PTG of x. This is the expectation of g of xt started from initial data little x. So we can represent the quantity which we want to estimate the derivatives of this quantity, and we have this representation. This is the probabilistic representation of the semi-group. And what we want to do is we want to differentiate the expectation at some time with respect to the initial data. So this has a very nice property in that it is very easy to couple two trajectories of this process from different initial data just by taking the same noise. So you take d x tilde t equal minus gradient of h of x tilde t dt plus square root of 2, but with the exact same noise. And now, what's the derivative of the difference? It's minus grad h of xt plus grad h of x tilde t. We don't have any noise here. This does not mean this is not a random object. It depends on xt and x tilde t, which are random. But in this expression of their difference, the noise only comes in as a second order object. It does not directly appear. And then you can take the initial condition for x tilde, getting closer and closer to the 1 to x, and formally, you can introduce a gradient operator. What happens if you differentiate with respect to your initial data in the direction v, a trajectory? And you get an operator, which I will call gradient. It's not a real gradient. This is going to be a random vector, which is going to solve the following OD, still random, d over dt of gradient xv of xt is equal to minus, when we let 2 go to 0, what we get the Hessian of h of xt applied to the vector grad xv xt. So I write this notation gradient x. It's not an operator applied to x. It's a random vector that measures the response to the response the dynamic makes to a small variation in the initial data. And this is okay. This is a differential equation. It's random. Xt is still a solution to a random process. But if you have uniforms bound on Hessian, you can make it disappear. And now what happens is that you can give a representation of the derivatives by differentiating through the expectation and making this operator appear. And if you do it a second time, you get a second order version of this that involves third derivatives of h. Now I'm being very formal. The proof that you can just differentiate across the expectation is not obvious. It uses stochastic calculus, and this is the core of Malliavin calculus for representing solutions to PD. And then, and then if you do this naively, you differentiate twice, you get a Hessian of G that appears. And then what you have to do is you have to integrate by parts. And there is an integration by parts formula for these stochastic differential equations, but on path spaces. You view the SDE as a function of an infinite dimensional Gaussian vector that gives you the noise. If I give you what BT here, this is a Brownian motion. If I tell you what BT is, then it's an ODE with this. So you can view this, the whole trajectory of your process, as a function of an infinite dimensional Gaussian vector. And you can do integration by parts with respect to the law of the Brownian motion. You do an integration by parts on the Wiener space. And this allows you to drop down a derivative at the cost of a factor 1 over square root of 2. Okay, so that's how it works. Now, I think I have a few more minutes. Yeah, just 2 minutes. Now, this strategy is not particularly, so I said it's not particularly Gaussian in nature. It's not particularly Euclidean either. You can also do this on Riemannian manifolds. You take your Brownian motion on a manifold, you take or Brownian motion with drift, and you look at regularization properties of the semigroup associated with Brownian motion. And the kind of results you get. So here, I said, okay, this is what you get on the Euclidean setting. If you do this on the Riemannian setting, you have to couple Brownian motion, so the noise on tangent spaces. You get an extra term, which is the Ricci curvature tensor. And if, because you have to do it twice on a manifold, by following this approach, you still get the third derivative of potential. And it will depend on the gradient of the Ricci curvature tensor. So the kind of results you get in the manifold setting are that if Ricci plus the Hessian of H is bounded from below by kappa, okay, this is kind of assumption that's familiar to many of you here. If the gradient of the Ricci curvature tensor plus the Hessian of H is bounded in a certain sense. And actually, I'm lying in that in the second order derivative, there are extra purely geometric terms that depend on the Riemann curvature tensor. So you end up assuming that the Riemann curvature tensor is bounded. Then you get Lipschitz maps from the reference measure onto a log Lipschitz perturbation of it. And if you do this on the sphere, just to make things explicit, if you look at the sphere of in dimension n of radius square root of n minus 2, sorry, n minus 1 sphere, rescaled by square root of n minus 2, this is the natural scaling in which we expect to get dimension-free estimates. What we get is that we get a map that is unfortunately not as good as the one we get in the Euclidean setting. Some of the terms that depend on the Riemann curvature tensor, we didn't see how to bound them optimally. But what we get is that exponential of pi times L, exponential of L squared over 2, Lipschitz map. So this is still dimension-free, only depends on L. But now we have a double exponential in L squared, and then probably this is not optimal. Okay, so yeah, though that's what I wanted to talk about. Thank you very much for your attention.
There are questions?
Yeah, they're not optimal. Sorry, I forgot to mention this. There is in dimension 1, there are also the optimal maps, but it's a fluke of dimension 1. In higher dimension, there are explicit counterexamples, examples between two Gaussians with different covariance matrix, where the two maps are not the same. So this is a result of Tanana. Sorry, I should have mentioned this from the start.
But Tanana doesn't cover the case where the target measure is the standard Gaussian.
Yeah.
But you can find example where the initial measure, so one of the measures is standard Gaussian and the other is not Gaussian, and in this case either it's not optimal.
It shouldn't be I mean, her example is Gaussian, but there is no reason why the two should be, and the fact that this already fails for Gaussian kind of suggests it should almost never be. But I should mention the linearization of the two maps are the same. At the linear level, if you linearize them, they're the same. These are two different ways of non-linearizing the Poisson equation.
So here you use the Ornstein-Lundbeck, and then you study the reverse flow map. What about using Langevin and studying the forward map that you get from this?
Sorry. No, so you mean what about other stochastic processes?
No, I'm saying, so yeah, so here you use, so you go from your measure to the Gaussian through Ornstein-Lundbeck, but you could go from the Gaussian to the measure through Langevin, right, with the right potential. Is that not, so like what's the difficulty with that?
I mean, the general structure is that you have your flow, and all you need to prove is a regularity estimate on the flow. Like if you can do this, this is good. And I mean, if you think of the transport map from yeah, so if your Gaussian is a Lipschitz perturbation of something else, this works. And this is just one example where it works. What matters is the regularity estimates. It's not something intrinsic of the direction, really.
You are in a completely different situation where H is non-convex,
yes,
but F is nicely uniformly concave. Can you do anything?
So there are other examples where this kind of results should work. For example, if the starting measure is not uniformly convex, but only so at infinity, I mean, it's harder, it's more technical, it depends on how far away it starts being convex, the quantitative estimates, but the general structure works. What I should say is some kind of compatible growth is necessary, because, for example, if you look at this Poisson equation, and you wonder, okay, I have H is still Lipschitz. For what kind of H are the solutions to this nice? Globally. Locally, they're nice, but I want a global estimate. And the answer is that for this to be true, H has to grow quadratically at infinity. It's a necessary condition. So you cannot do this with anything.
Thank you.
Are other questions? Okay, if not, let's thank again. And we resume after the coffee break at 4:30. Of this afternoon is Simone Di Marino. He will speak about Synchron meets Poincaré. Thank you.
Thank you very much for the introduction and the invitation. So, yes, we will talk about Synchron and the speed of convergence of Synchron, which will meet Poincaré inequality in the end. So we will touch the Poincaré inequality just in the end. So this is a joint work with Saverio Salzo and Vladimir Kostic. So this is a work in progress. Actually, it's more or less finished since 1 year and something, but we didn't finish to write it. But okay, I will try to explain. So fortunately, there was already Guillaume that said something about the entropic optimal transport. So I will go more or less fast on the introduction of the main character. So let's start with the classical optimal transport. So the classical optimal transport, we have these measure mu probability on a space X and mu probability on a space Y. We stay rather general. And our cost between mu and nu is the minimization of some cost function, which is general at this point, integrated over d pi, where pi are the usual transport plans. What is the entropic optimal transport? Is very similar to the classical optimal transport, but we add this red penalization, where the idea is that
as all of you know, in regular cases, for example, the square distance, usually the transport plan is concentrated along the support, the graph of the optimal transport map, and so it will be a measure which is concentrated, on a lower dimensional set. Adding this entropic penalization grants us that our optimal plan now for this entropic optimal transport problem will be diffuse, and in particular will be absolutely continuous with respect to mu times nu. And so it's suitable, for example, for numerical computations. As we saw in the talk of Guillaume, of course, the cost, as epsilon goes to 0, the cost converges to the optimal transport cost. And with it, there is convergence also of the potentials. We will see in the next talk the gradient of the potentials, and also the optimal plans. So, as I said, why we introduce this entropic optimal transport? Because for computational reasons. And the idea is basically, once you want to compute something which is a minimizer, you try to use some optimization, right? Now, if you try to optimize a linear function, this you have to use, the simplex. It's not as easy as it seems. It's much easier if you have some strongly convex function. And now the idea is that since the entropy is strongly convex, now we end up here with a functional of pi, which is strongly convex. And so we can use any optimization algorithm that we want, and we will grant a good convergence. And the algorithm of choice in this case is synchron, aka IPFP, aka alternating point projection, aka dual ascent, and there is a plethora of names that you can attach to this algorithm, because it's a very simple algorithm, we will see, which is general in many situations. So, and in particular, I will concentrate in synchron algorithm as the block dual ascent of the dual problem of entropic optimal transport, because it gives the right point of view for the optimization, I think. So we write formally, if you want, the dual of the entropic optimal transport, which will be just maximization over the potentials phi and psi of the classical two pieces which comes from optimal transport. So integral of phi d mu plus integral of psi in the nu minus now this very ugly thing which comes from the dual of the entropy. Right? Okay, and now these you should think, if you want, as the penalization as a soft constraint of the type phi plus psi must be lower or equal than c. Why is that? Because if you imagine that you have some couple of points x, y, where phi of x plus psi of y is greater than c of x, y, then here you have exponential of that number divided by epsilon, so it's huge. And now if you subtract it and then you want to take the maximum, of course it's not good. And so the idea is that this is a softening of the hard constraint that we have in usually dual optimal transport, which is phi plus psi less or equal than c. Okay, and now the idea is very simple. Now we have this functional of two variables, phi and psi. So what can we do in order to maximize it? Okay, we have to maximize with both phi and psi. Now what the block dual ascent does is basically you choose one of the two variables and you do maximization only on that one, fixing the other one, right? So, for example, let's take phi to be fixed and then we optimize over psi. What does it happen? We have to optimize just this guy, these two guys here, because the first one is fixed, so we don't care. And in order to optimize this, okay, we group all together, we split this with Fubini and we do the integration over the nu here. and we write it like this. Now, what is nice about this, now it's just a function of y, which depends on phi, of course, but it's just a function of y. And so we get that we have to maximize this. And now this is why this is nice, because this we can optimize y by y. Okay, so the function, the psi optimizing y, it depends just on g and y. Okay, how can we do it? So we just take these as like t minus epsilon e to the t over epsilon times g over y, and we optimize in t. We take the derivative. Take the derivative, and we get that the optimal value for psi at the point y will be just minus epsilon log of g of y, which we write like this. It can be written like this, which is what Guillaume wrote. And now this can be seen in a similar way that we saw before. This is just a soft mean of this function here. So the soft mean in x, right? And again, as epsilon goes to 0, this soft mean converge exactly to the mean, and the mean of this function here is actually the C transform of phi. So this is what we call the C epsilon transform. So it's an approximation of the C transform. And now the nice thing about this C epsilon transform, which has been observed in several papers, is that as in classical optimal transport, we can carry regularity properties of C, of the cost function, to any C epsilon transform. What do I mean by that? If C is omega continuous, for example, is Lipschitz, then also phi C epsilon will be Lipschitz with the same Lipschitz constant. And the same is equal if C is bounded, then the oscillation is bounded. And if C is lambda concave, then also phi is lambda concave. So we have all the regularity property, the easy regularity property coming from the C transform. Okay, and now this is nice because of course we get compactness because as soon as we do a say epsilon transform, and we do also the C epsilon transform for the other one, we get two say one Lipschitz functions. Since one Lipschitz function are compact in the by Ascoli-Arzelà in the L infinity norm, we get that very easily there exists a maximizer. And now, since this is strictly convex, it's much easier to see that if we get a maximizer, then these will be equal to the primal value. And we have also, as Guillaume wrote it, we have also the expression for the primal optimal yes, if C is lambda concave, then this is lambda concave as well with the same lambda. No. So it depends if you take like x minus y squared 1/2, or so it depends on the definition that usually there is a gap between the two in the square case, just in the square case. And so we get that pi epsilon star is actually equal to e to the phi star of x plus y psi star of y minus cxy divided by epsilon times mu. So we have this rigid structure that says precisely what is the relation between the minimal plan and so the optimal plan and the optimal potentials. Okay, now what is the Synchron algorithm? The Synchron algorithm is explicitly continuing doing this C epsilon transform. So if we start from phi 0 psi 0, then the next step will be, okay, let's say we fix phi, and then we take here phi 0 C epsilon transform. And now here instead we fix psi, which is, by the way, equal to phi 0 c epsilon. And then here we put c epsilon, and again, right? So this is phi 2, this is phi 2 c epsilon. So alternatively, we maximize on one function or the other. Now, of course, one could do this also in the classical optimal transport. What happens in the classical optimal transport? Well, here you do the C transform, here you do the CC transform, here you do the CCC transform. But what do we know? The CCC transform is equal to the C transform. So in the classical optimal transport case, here after 3 steps we stop and we don't gain anymore, right? In the epsilon strictly greater than 0 case, instead we continue indefinitely. Okay, just let me write this. Phi is psi 3, psi 3, c epsilon. And what does it happen? That we have this dual phi 1, psi 1. This will be less or equal than the dual phi 2, psi 2, less or equal. This is by construction, of course, because I'm taking the 2 couple and I optimize and I maximize on one of the 2. So I'm gaining always. And what you can prove using again the compactness is that actually this sequence will converge in L infinity. And once you converge in L infinity, you then in the end use the fact that your sequence was coming by C transform. So in the end you get that any limit point must be such that if you do the C transform, you remain the same couple. And doing the C transform and remaining the same couple is equivalent to having this relation here. So you stop and you converge. This proof of convergence, unfortunately, is just by compactness, so you don't have any rate. You just know that converge to the right guy, and by the compactness in Ascoli-Arzelà, you know that converge in L infinity, so the potentials are converging strongly, but you don't know the rate. So why are we interested about the rate? So we are interested, of course, because as I said at the beginning, this is for numerical purposes, if you want, right? So if the rate is very bad, let's say the rate goes like, I don't know, 10 to the minus 10, then this synchron algorithm will not be useful because you have to wait an eternity just to have something. So the idea of looking at the rate of convergence is to see whether if this algorithm is useful in real life or not. Of course, the practice comes before the theory. And so from simulation, you see that actually it seems that you get the convergence as soon as the number of iterations is much greater than 1 over epsilon. So here I wrote just a possible definition of rate of convergence. In this case, the rate of convergence, so I want an exponential rate of convergence, so exponential in a number of steps, and here just is the convergence of values in the dual problem. Okay, and this will be my rate of convergence. Why this is the rate of convergence? You have to think of it as a speed of convergence, right? So if eta epsilon is epsilon, okay, if the speed is epsilon, in order to get far away, I need to wait a time which is 1 over epsilon. Okay, so the speed of convergence is something small, and if it is too small, then it means that the algorithm is super slow. Okay, so and this is sorry that this is just below. This is a personal communication of Marco Couturi. So thanks to Marco Couturi, 3 hours ago, we did this little plot, which is really epsilon. This is epsilon. It's a log-log plot, and this is the number of iterations that you need to get at a certain threshold. Fixing at a certain threshold that here I don't remember what it was, but fixing at a certain threshold, you see that in fact in the log-log scale you have a linear decay, and actually the slope you see that if you connect the dots of 10 to the minus 3, 10 to the 3, this one and this one, you see that this is pretty parallel to that one. So actually here you see that the number of iteration k should grow like 1 over epsilon, right? So the speed of convergence by simulations, it seems that it's faster than epsilon. Okay, of course, cannot be too fast, because as we saw, as epsilon goes to 0, we have to have that at epsilon goes to 0. So the speed of convergence should go to 0, because as epsilon goes to 0, our algorithm stops after three steps, right? So it freezes. So it cannot be that the rate of convergence stays some velocity. So other estimates from below. So this is an estimate from below. If you want the best ones that one can hope, at least this is what we see numerically. What has been proven? Yeah, well, it has been proven that this rate of convergence is greater or equal than e to the minus the L infinity bound on the cost divided by epsilon. And now if you think just a bit about it, this speed of convergence is horrible. Because just you think of the cost that is quadratic on the square, right? So C infinity is just square root of 2. And you take epsilon, which is, I don't know, 0.1. Then this becomes e to the minus 20. Let's take 0.01. This becomes e to the minus 200. E to the minus 200, it means that you need e to the 200 steps, which is a lot. You just lower a bit and you get much worse. So this is far away from the epsilon that we see numerically. So we will see in the end why is that. And a recent paper by Guillaume showed that this estimate is true even in the multimarginal case. Why multimarginal is interesting? Because again, multimarginal, for example, can be interesting to look for a solution of the Euler equation or the density functional theory. So there are several application barycenters. So there are several applications which can be interesting also in the multimarginal case. And I say it explicitly because actually from the proof here with the contraction in the Hilbert metric, actually the rate is fairly more or less explicit, but not explicitly tied to the marginals. But it can be made explicit. Convergence in the multimarginal case was still open up to the paper of Guillaume. Okay, so these are the estimate from below. So it's at least as fast as this. But the other thing is that by a paper of Berman, there is also an estimate from above. So this Sinkhorn algorithm cannot converge too fast. And now I will explain a bit this, because the result of Berman, maybe it's not widely known. I think it's very nice. And I want to explain why it gives this kind of estimate. So because so this is the theorem that Berman has in his paper. So it's basically dealing again with convergence of the Sinkhorn algorithm. So he has also a grid, and he's doing k that goes to zero, k that goes to infinity, epsilon that goes to 0, and the grid that goes. So the step of the grid which goes to 0. So we eliminate the step of the grid. We don't care. But still, we have this epsilon that is going to 0 and k that is going to infinity. What he claims what he proves is that so there exists a family of evolving potentials phi t, such that now if I take here you have to imagine k is going to infinity and epsilon is going to 0 in such a way that epsilon k stays finite, goes to some t, and the idea is that this which is the kth iterate of the synchron algorithm with parameter epsilon, this goes to a fixed phi t, if you wish, which does not depend anymore on epsilon and k. Okay, what it's saying is that if I do I don't know 5 steps with epsilon, which is 1 over 5, this is roughly the same as doing 10 steps with epsilon equal 1 over 10. This is the same as doing 100 steps with epsilon equal 1 over 100. These are converging to some phi t, and now the very nice thing is that this phi t is actually an evolution by something which is of course linked with Monge pair. So we have that this parabolic evolution equation fully nonlinear is true. So this is evolving according to the logarithm of determinant of identity plus d squared phi t minus g minus f, where f and g are like it's so mu is equal to e to the minus f and nu is equal to e to the minus g, and f and g are nice and bounded. So as I wrote here, this works just for the square cost, square distance cost, x and y which are on the torus, and mu and nu satisfies the hypothesis by Caffarelli. So it's bounded away from infinity, away below from 0 and above from infinity, and they are also Hölder in such a way that you have some control on the second derivatives of phi, basically. Okay, now why this, which is a convergence theorem of both epsilon k, etc., says something at epsilon fixed, if you want. Okay, it doesn't say something at epsilon fixed because, as you see, this goes to infinity, but it says something as epsilon is going to 0, eta epsilon cannot be too large. So the idea is that eta epsilon must be less or equal than c epsilon as epsilon is going to 0. And we prove it just by contradiction. So from some point on, this should be true. Why this is true? Well, suppose that there is some eta epsilon such that the sequence of epsilon goes to 0 such that eta epsilon is much greater than epsilon. Then I choose k, which is 1 over epsilon. And then from one side, I can say that this, thanks to the assumption that my speed of convergence is at epsilon, now this is going to 0, thanks to the assumption that at epsilon now is faster than epsilon. But then this is going to what? This is going to the limit of this guy here, but this guy here is again the cost epsilon, but the cost epsilon, as epsilon is going to 0, we know that is going to the cost. So this is going to the cost, so this is going, if you want, to the dual, sorry, what is this? Dual 0, phi star psi star 0. Okay, the optimal potentials for the optimal transport problem, classical, so epsilon equal to 0. On the other hand, since now we know that this is going to 0 thanks to the estimate of Berman, now epsilon equals to, k equals 1 over epsilon, this is going to 0, right? And so this means that this is going to 0, this is going to 0. This is in the infinity norm. But now this, again, now is going to what? But, well, these are very nice behaved, these functional with respect to the potentials. If they are converging, this is going to d0 of phi 1 psi 1. But now these two are of course different because phi 1 psi 1 is just okay, I'm doing the evolution of this for time 1, but this is going, yes, it is going exponentially fast to the solution of the optimal transport problem, but just for time equals to infinity. for time equal to 1, I cannot be the optimal potential. So this cannot be true. Sorry, this is not CVD, this is absurd. Okay. So in this way, what we showed basically is that, so numerically, it should be as fast as epsilon. We have a case in which it cannot be faster than epsilon. So we would say that, okay, for the general case, it should be like epsilon. So basically, if you want now, we want to generalize what Berman did. And we want to generalize it in a bit, so in a general way, meaning that we want the cost function more general, and we want also to be able to use the multi-marginal case. So the goal now is as an asymptotic rate of convergence, so as k is going to infinity, as a function of epsilon, and we are interested in the regime when epsilon is going to 0. Okay, and now the idea, which comes from, okay, yeah, it's below. The idea is that, okay, now we are interested in this rate of convergence, so I shift everything in such a way that the functional is going to 0 and variables are going to 0, right? In such a way that I can do maybe a Taylor expansion. So what do? We take the difference between the epsilon phi psi minus the optimal one, right? So we write it like this. And now here we take the new variables. Now the new variables, which are the ones that will go to 0, are phi minus phi star, and psi tilde, it's psi minus psi star, right? Now this is okay. And here, now here, when I add and subtract phi star, okay, when I subtract here, I get phi star and psi star. When I add, I get phi star plus psi star minus c over epsilon times mu times nu, which is precisely the optimal transport plan p epsilon. Okay, I'm just using the optimality condition. And now this, I can write everything as, so mu and nu are the marginals of p epsilon, so I can write this as just an integral of f epsilon phi tilde plus psi tilde, where f epsilon is something like this. Okay, trust me on that. And now this, when t is small, it behaves like what? So you do the Taylor expansion, this is just t squared divided by epsilon. Now, the main idea is what? As we said, phi k is converging in L infinity to phi star. Psi k is converging to L infinity to psi star. So when I'm looking at this functional for psi tilde and psi tilde, they will be very small in L infinity norm. So actually this Taylor expansion makes sense, and we see that also the synchron, so the synchron of the Taylor expansion is the linearization of the synchron. Okay, if I do the dual ascent of the of this quadratic approximation, this will be the linearization of the synchron algorithm. Everything is converging, and so this is why I'm looking at this linearization. So I'm looking now at this functional here, which, if you wish, it's much nicer. Why it's much nicer? Because it's quadratic. This is a quadratic functional, and I'm minimizing the quadratic function. Minimizing quadratic forms has a plethora of literature, and in particular it's related to, in this case, into alternate projection in Hilbert spaces on linear spaces. And there is a plethora of literature on that, and we'll see in a while what happens. Just to be aware, so now this is just a justification in order to why I'm studying the linearization. Then in the end, the result, the end result that will deal only with the entropic regularization doesn't have to do this kind of linearization. This is just to explain what is the idea behind, but then the calculations are done directly on the real synchron with with the entropic function. Okay, and now I write it like this. So the theorem that we prove is that if this function of VMC is bounded from below by eta times the L2 norm squared of phi plus the L2 norm squared of psi, then the alternate minimization of this guy here, now it's minimization because here I add the minus, and I'm doing calculus of variation, so I prefer minimization, I don't want to do maximization. This will converge exponentially with rate eta. Okay, and now why is this? Because basically, very basically, and converge exponentially with rate eta with respect to the L2 norm. So everything is converging. So the L2 norm of phi is converging to 0, the L2 norm of psi is converging to 0, and the functional is converging to 0 exponentially with rate eta. Why is that? Because basically, if you want, f is quadratic. F, yes. This is just, so if you want this, yes, it's local convergence, but it's just to justify why then the Poincaré constant will appear. In the end, so this is some magic that is happening behind. What I did is precisely this. So, okay, I linearize and I say, okay, linearization, you have this rate. And then I say, okay, let's try to do it globally. And fortunately, everything goes well. And it's magical. And you have the same rate of convergence also at the global case. So basically, this that in this case, this can be seen as a bound from below. So it's strictly convex with eta. And this is obvious, right? That the second derivative of this guy is bounded by eta. It's obvious because it's just a definition, if you want, in 0. And then this is quadratic. Since this is quadratic, doing it in 0 or doing in any other point is the same. It's just a quadratic function. And the convergence with rate eta is, again, if you want, obvious for any kind of optimization algorithm that you put. If you are strictly convex with bounded below from eta, then the error of convergence is at least eta. Okay, as I was saying, so in this case, if you want, is a bound from below of the whole second derivative. In the case when then we do it globally, is some kind of, you have to interpret it as a kind of Polya-Loyazievich inequality around just the minimal point. So in the end, you get the same rate convergence, but you are not using the second derivative globally bounded from below. This is what in the paper Carlier does, and so you get this bad rate. Instead, here you're looking just around the minimum, and you're using Polya-Loyazievich. Okay. So this is with convergence rate eta. Now, the idea is that now we reduced basically our search for the convergence rate to the search for, okay, what is the optimal eta that I can put there, right? Are you more or less convinced? And this, in the case of the linearized version, this is precisely an if and only if, because again, this bound from below is attained in some directions, and so I can approach the minimum in those directions, and here I will get precisely the rate eta. So this is sharp, at least in the n equals 2 case. This is also true for the multi-marginal case, but I do not have the proof, at least I did not find the proof where this eta here is actually the optimal rate. If you have the optimal eta here, it will be of the optimal rate, even in the linearized stuff. Okay, and now we want to understand what is this eta? How can I calculate this? And the idea is very simple. So this is pi 0, right? So this is x and y. This is pi 0, which is my ideal optimal transport, which is as usually I imagine it concentrated on a map. And now pi epsilon is just a bit larger, right? Now, what is the geometry of this being larger? This is something that Guillaume did in his calculation. So the idea is to look at how large this is. Now here you have to imagine if you cut here, you see something like this, right? Now what is the shape of this? It's precisely this one, right? So it's e to the phi star plus phi star plus psi star minus c over epsilon. And now we want to understand how large is this guy, right? In order to understand what is the kind of diffusion we are using. So how large is this? What is the width of this Gaussian in some sense? And so if you put, so if you say that in T of x you have the maximum, right? So if in y equals T of x you have a maximum, then here, okay, here there is a second derivative. So there is this minus second derivative of this xx yy xx of c. Okay, so you have something like this. If you develop, you know, the second derivative, we are assuming, if you want, that c is c2, right? And this is a very similar calculation that does also Sumik Pal, and the spirit I believe it's similar to what Guillaume was saying. So you can approximate this as the Taylor expansion at the second order. And now, how large is this Gaussian? Now, this Gaussian, you imagine, okay, I cut it at level, I don't know, 1/100 or something like that. But this is large, like square root of epsilon, because you have to put here this equals to some number. So it's square root of, it goes like square root of epsilon. So it's square root of epsilon is the distance, the maximal distance between x and t of y. So this is to understand what should be the geometry, right? What should be the geometry of this guy here. And now, if you take this inequality, now we want to understand what is the optimal eta, and now we choose some specific psi. Now, let's fix phi, and now I choose a specific psi. Psi I take as phi of t of y. Okay, this guy here, phi of t of y. Now, what happens is that, and at the right-hand side, you get integral of phi squared plus integral of phi composition with t in d nu, which is another time integral of phi squared in d mu. So at the right-hand side, you get this. And what you get on the other side, you get something like this. Yeah, you have to take minus, of course. Minus phi of tx. And now this is phi of x minus phi, ty. Okay, something like this in the pi epsilon. And now we know that now what is the range where this is active. So where is pi epsilon active, but where x minus ty is of order square root of epsilon. So what happens is that this squared becomes something like this, because it's active only when x and t of y are close. So I'm doing again a Taylor expansion here. And now this is more or less, so the norm, so now I'm doing the integration of basically a second moment of this Gaussian here. And now I do the second moment, and I get epsilon, which comes from the fact that this is at width, which is more or less square root of epsilon. And then I get the modulus of the gradient squared in d mu. So in the end, collecting everything together, what do I get is precisely this inequality here. So the integral of the gradient squared is greater or equal then eta times this divided by epsilon. Okay. Now you imagine that this, as epsilon is going to 0, this should hold true, but then this is saying that eta epsilon should be at least should be less or equal than the Poincaré constant times epsilon. I'm saying the other way, so it's Poincaré constant should be at the denominator, I believe, right? So if my measure mu doesn't satisfy a Poincaré constant, of course this cannot be true. Right? This is saying that phi, so mu satisfies a Poincaré constant. So if it doesn't satisfy, this should be less or equal than 0. So if Cp is plus infinity, this should be 0. Okay, so we have this kind of inequality. What are we saying? Well, we're saying that as epsilon goes to 0, you cannot be fast as epsilon if mu doesn't satisfy a Poincaré constant, if mu has not a Poincaré inequality. Okay, this again is sketchy, and it's just a computation to understand that the Poincaré constant is involved, most probably, and this is a way to say that probably if mu doesn't satisfy a Poincaré inequality, then the rate should be less than epsilon. And okay, and in the end, what can we prove? We can prove this. Now this is not really the same order, but it's similar. So suppose now that you have the same inequality here, but now here with the full really entropic functional. Suppose that this is true again with eta, then the rate will be exponential with rate which is epsilon eta, and this, I believe, it's optimal. Poincaré is sufficient. Poincaré is sufficient is saying that if the cost now is L Lipschitz, and this is what really we prove, this is L Lipschitz, and if both marginal, of course, that has to satisfy the one Poincaré inequality in that case with constant Cp, then we can take in this inequality, we can take eta, which is greater or equal than Cp epsilon over L squared. So it's really so it's depending linearly on epsilon, and so the rate of convergence, since here I have another epsilon, is greater or equal than epsilon squared. So what we did here by hand waving, if you want, is that at epsilon should be less or equal than epsilon. What we prove is that the rate of convergence is greater or equal than epsilon squared. What are we losing? We are losing the fact that since we are assuming only that the cost is at Lipschitz, we cannot use the second derivative here. We just use the first derivative, and so we get just x minus ty modulus over epsilon, and so if you do the same calculation, you will get here epsilon squared. Okay, I think that's it, and thank you for the attention.
Time for a very short question.
So could you come back to the theorem? Yeah? So what is epsilon? I'm not sure I get the hypothesis right.
What is f epsilon?
Yes, what is the left hand side?
Yeah, f epsilon was this guy here.
Oh, okay. So and then this implies a global convergence rate. So it's really for each iterate you have this.
Yes, exactly. Yeah. And this is true also for the multi-marginal case. You lose a factor n somewhere, but.
And if this hypothesis is violated, you say that you think that the rate would not be epsilon somehow. I mean,
the rate. So if you don't have the Poincaré constant, I believe that analyzing better than the linearization, you get that the rate cannot be epsilon. But we are talking really at the exponential rate. So you're looking at k, which is plus infinity. So usually what happens is that you use just k, which is 1 over epsilon, and there, up to there, you don't see the exponential rate. It's just polynomial. It's 1 over k.
Okay, thanks. Because the general rate, I mean, there is a simple lemma that proves that it's 1 over k, but then you get...
Exactly.
I have a question about the expansion you did to get the Gaussian. So do you need then smoothness on your measures? Because you were using some uniform convexity and smoothness of the potential.
So this was just to justify that Poincaré constant is probably needed. But this is not, this is just to convince you that the Poincaré constant is probably needed, but we don't do this calculation actually.
Okay, so there is no smoothness assumption.
No. Here, the only thing that we prove is this one actually. The other one was just hand waving to convince you that Poincaré constant is probably needed because of that. But
so I'm intrigued by this continuous time phi t that you have. So associated to phi t and psi t in this Berman paper is a coupling, say pi t, that converges to pi star epsilon. Do we know anything about whether this is following some continuous time gradient flow or is describing the marginal of some stochastic differential equation or anything like this?
I don't know. I don't know. In the paper of Berman, I think it doesn't say anything also. I'm not so sure.
And you think it's actually the Poincaré constant of mu and nu that shows up rather than the Poincaré constant of pi star epsilon that actually shows up?
Poincaré constant of pi, I don't know. I'm pretty sure that, there are some caveats. Actually, so this should tell that here I'm working just with mu. And I'm basically saying, okay, mu should have a Poincaré constant. And so also nu should have it. But it's not, so it's not entirely clear. If you watch what it happens actually, is that when you do the alternate maximization, basically you take phi hat, which is the optimizer, then you are spreading the values of psi according to pi epsilon. Then you do another C transform, you're spreading with pi epsilon transpose. And so in the end, you get that if you do the 2 iterates, then you get that psi n plus 1 is just an operator applied to psi n, and this operator is pi epsilon transpose if you do it in the discrete, right? So now it depends on what is the eigenvalue decomposition of pi epsilon transpose, and this is not really so. It's not so. So I'm not so sure because if you think of it as a connectivity result. Because Poincaré constant is a quantitative version of how disconnected or connected is the support of mu and nu. Now, if mu is disconnected but nu is connected, when you do pi epsilon transpose, the connectedness of nu goes a bit into nu, and so maybe you can get it away with just the Poincaré constant of one and some regularity of the other, but I'm not so sure on that. So.
Okay, so thank you again, Simone.
Yes.
And we conclude this afternoon session with Luca Tamanini speaking about gradient estimate for the Schrödinger potential and convergence of the Brenier map.
Okay, so thank you very much for the introduction and for the invitation, which gives me the possibility to present this recent work obtaining collaboration with Alberto Chiarini, Giovanni Conforti, and Giacomo Greco, who is here in the audience. And aim of this paper was to obtain some general gradient estimate for Schrödinger potentials, and as an application, prove convergence of the gradients of such potentials to the Brenier map. And we also had a second application, which is some new quantitative stability result for optimal couplings and cost in the Schrödinger problem, but I'm afraid I will not have time to present also the second part. So let's start with the first part. Actually, let us start by defining the Schrödinger problem, because I would like to, it's good to know that even if it has many analogies with entropic optimal transport, is not precisely the same problem in general. So let us start with the physical definition, the physical thought experiment provided by Schrödinger in his 1931 paper. And the idea is the following: assume that we have n IID particles, which evolve according to this diffusive SDE. At the initial time, they are sampled according to the invariant measure, and we denote by mu Tn the empirical distribution of our particle system. Then, by virtue of this SDE, if the initial configuration is close to some probability mu, we expect that at some final time t, the empirical distribution should be close to pt mu, where pt is the Markov diffusion semigroup associated to this SDE. Okay, this also means that any probability nu different from pt mu is unlikely to happen, to be observed at time t. Okay, still, since we are dealing with a finite number of particles, it's still possible, even though the possibility is small. Okay, so assume that at the final time we actually observe some nu different from pt mu. Okay, this means that while we were looking at the systems, something improbable but still possible happened, and therefore we want conditionally on this observation to determine, to reconstruct the most likely evolution that drove our particle system from mu to nu. Okay, so it is a problem of rare events of maximal likelihood, so large deviations are involved, and by means of Sanoff theorem, it's possible to prove that the probability of this joint event is exponentially small, and the function that determines the smallness, which is the rate function in the large deviations principle associated, is this calligraphic C, which is the optimal value of an entropy minimization problem, which is what is called Schrödinger problem. Okay, so one aims in this problem, one aims to minimize the Boltzmann entropy among all couplings between mu and nu, and the Boltzmann entropy is considered with respect to the joint law at the initial and finite time of our process X. Okay, and this problem can actually be lifted in an equivalent way in a dynamical way to the path space if one wants. Okay, this also suggests some difference with respect to EOT and Schrödinger problem, because usually EOT is just a purely static problem, while Schrödinger problem is admits a dynamical interpretation. Okay, but that's not everything. Okay, let's say already at this physical level, let me say, one can guess the connection with optimal transport. Okay, because the capital T here, that here is written as a time horizon, after rescaling to 0, 1, capital T can be interpreted as a temperature parameter, and in this way, as T goes to 0, it can be it happens here, it just rescaled here is in the Brownian motion. It appears in the diffusion of the Brownian motion. So it can be interpreted as a temperature parameter, and in this way, as T goes to 0, we expect, our particles are we are freezing our particles, so that we are aiming to send mu onto nu in a way which is more and more deterministic, and in the limit is purely deterministic, which is precisely a transport problem. Okay, but there is also several mathematical ways to see this connection. Indeed, after the several contributions by Léonard, Chen Giorgio Pavone, Gentil Léonard Ripani, and myself and Nicola Gigli, it has been noticed that if one, the rescaled entropic cost, so the rescaled optimal value of the Schrödinger problem, can be represented in several equivalent ways. For instance, in a Benamou-Brenier-like formulation, where the action consists of a kinetic part plus a perturbation, which is given by the Fisher information, and other dual formulation a la Bobkov-Gentil-Ledoux, and this dual formulation. So, for instance, in this way, at least formally, one expects that as t goes to 0, this perturbation disappears, and therefore one recovers the classical Benamou-Brenier formulation for the Wasserstein distance. Okay. And so, building on top of this consideration, the small time behavior of the Schrödinger problem has been investigated. And in the recent years, there has been a huge literature that studied the small time asymptotic of the cost. These papers have been already cited before by Guillaume, so I will not cite them again, but I mean, are here listed nonetheless. But I mean, besides the cost, there are other quantities that deserve to be investigated in the small time limit. So, for instance, the potentials. Okay. Schrödinger potentials are defined to be solutions to this dual Schrödinger problem. Okay, let me say that after César and also works by Rüschendorf-Thomsen, Borwein-Lewis Nussbaum, and Léonard, it is well known that this problem admits an essentially unique optimal couple, phi t psi t, and this optimal couple, I mean, unique up to multiplication by constants, okay? And this unique optimal couple is linked to the unique solution of the primal problem through this identity that is that already appeared, but in the context of EOT in the talk by Guillaume. And okay, with this said, the question now is what happens to the potential, to Schrödinger potentials as t goes to 0? A first result was obtained by myself and Gigli, but under additional assumption on the marginals, assuming that they have compact support and bounding densities. But the general case was settled by Nutz and Wiesel in the case for the entropic optimal transport problem, so whose dual formulation reads as follows. And as you can see here, I mean, it is close to the Schrödinger dual Schrödinger problem, but is not precisely the same thing. Okay. Nonetheless, the Schrödinger problem can actually be recast as an entropic optimal transport problem by choosing a cost which is of this form. Here, Pt is the density of R0t with respect to the invariant measure times the invariant measure, so the transition kernel of the process. And okay, and here we added some terms depending on the marginals. So, however, the main difference is the fact that usually in EOT, the cost is fixed, while if one wants to write the Schrödinger problem as an EOT, the cost explicitly depends on t. Okay, this means that while the result by Nutz and Wiesel stated for EOT is requires essentially nothing for the convergence of L1 for the L1 convergence of potentials, if one considers the Schrödinger in the a time-dependent or t-dependent EOT problem. In the same paper, there is also a result that deals with this case, but of course one has to add to verify some assumption on the cost, which depends on t. So, as a first step, together with my co-authors, we verified these extra assumptions required in the paper by Nutz and Wiesel. So let me also, by the way, now state precisely the framework we are working within, because I did not say it so far. So we are in a smooth weighted Riemannian manifold, satisfying some curvature dimension condition, and is possibly infinite, but in this case we assume the measure M to be a probability. Then we take two marginals with finite moments and finite entropies. And then, under this assumption, we have that the potentials phi t are a strongly precompact family in L1 mu, and okay, any accumulation point is a Kantorovich potential from mu to nu. And an analogous statement holds for the potential psi. Okay, this result is proved essentially heavily relying on Nutz and Wiesel. The assumptions that are required on the cost that I mentioned before are essentially two. First, one needs to prove that, in our case, minus t logarithm of pt converges locally uniformly to the square distance, which is somehow the cost, the limit cost, in a sense. And this is true by a beautiful result by Norris, which establishes locally uniform Bharadhan estimate for the heat kernel on weighted Lipschitz manifolds. And the second condition, we need to bound from above our cost with some function c bar, which is of this form and has the right integrability. And this can be proved using heat kernel lower bounds, which in the finite dimension are, for instance, proved in the paper, in a series of papers by Sturm and Dirichlet forms, and in the infinite dimensional case by Wang, where, however, the finite measure condition is required. That's why we add it. Okay. So the L1 convergence of the Schrödinger potentials is proved. Let us now pass to the main goal of our one of the main goal of the paper, which is the strong convergence, L2 convergence of the gradients. So in this case, we are in the same framework as before. And now on the measure mu, we assume that some extra assumption. We ask that its density is locally bounded away from 0 on the interior of the support. We assume that the boundary of the support is negligible, and also that mu has finite Fisher information. This is required in order to be so that the gradient of phi t is well defined. Okay. Okay, under this assumption, we have that the gradient of phi t, as already anticipated, converges to the gradient of any Kantorovich potential from mu to mu, strongly in L2 of mu. And the proof essentially consists of 3 steps. First of all, we prove weak compactness of the gradients in L2 mu. For that, we use this identity here, which follows from this identity just by taking the projection on the first marginal and then the logarithm. Okay, we have this identity here where psi 0 t is the Hopf-Kohl transform of the potential psi. And then using this identity, we can estimate the gradient of phi t with the Fisher information of mu, which is therefore needed to be finite, plus the gradient of the Hopf-Kohl transform of psi. And this second term here can be estimated by means of what is called corrector estimate, which will be discussed later on in a couple of slides in a better way. But now, combining this inequality here with this one, we see, and recalling also that TCT converges to the squared Wasserstein distance, we have this first inequality here that bounds from above the gradients of phi t as desired. Now, as a second step, we first observe that we can find a Kantorovich potential phi 0 and some vector field zeta, such that phi t up to subsequences, phi t converges to phi 0 in L1, and the gradient of phi t converges weakly to zeta. The first information is just a consequence of the previous proposition, while the second one is a consequence of the first step. Now we want to change this, pass from this strong L1 convergence to weak L2 convergence, with at least on sufficiently small balls with respect to the volume measure. And to do so, we use the fact that compactness in L2 with respect to mu implies compactness in L2 with respect to the volume measure, thanks to the fact that mu, the density of mu is locally bounded away from 0. And then we use the fact that the volume measure restricted to a sufficiently small geodesic ball satisfies a Poincaré inequality. In this way, the compactness of the gradient implies compactness of the potential. And then having small
having weak L2 convergence here, one can deduce that this zeta is in fact the gradient of phi 0. Then, observing that the Brenier map is unique, there is no need to pass to a subsequence actually. And the third step is just an easy fact in Hilbert spaces theory, because we have just by lower semi-continuity of the norm, we have this inequality, which together with the one written here below gives convergence of the norms, and convergence of the norm plus weak convergence gives strong convergence as desired. Okay, now let me discuss in more details this corrector estimate that I mentioned before. Here, the assumptions are the same as in the previous theorem, except that we do not assume finite Fisher information on mu. And then we can control, as I said before, the gradient of the Hopf-Kohl transform in terms of the entropic cost minus the entropy of the first marginal. So let me comment why this is called corrector estimate. This is due to the fact that the entropic interpolation, which I did not define, but okay, is the unique solution of this Benamou-Brenier-like problem. This solution, this interpolation here from mu to nu, of course, in the previous variational representation is a solution of a continuity equation, but it can also be seen as a controlled gradient flow with control given by the gradient of psi t. What do I mean by this? I mean that rho t solves a Fokker-Planck equation with drift given by the gradient of psi t, and psi t solves an Hamilton-Jacobi-Bellman equation. So much like in the control theory, in the classical control theory. And let me also say that estimates of this kind appeared in two previous papers by Conforti and myself, but always with additional assumptions on the marginals. Here, instead, we were able to remove any any non-required assumption on mu and nu. It was indeed a quite technical part. And let me also say that these kind of estimates are very useful, not also for ergodic behavior of the underlying particle system, since they allow to obtain quantitative Turnpike property. By Turnpike property, I mean that is a classical behavior in control theory, which in this setting essentially means that the entropic interpolation, when t is very large, starts from mu with a huge acceleration, spend most of the time around the equilibrium, which is the invariant measure, and then only at the very end goes back to nu, to the second marginal. And this behavior can indeed be described in a quantitative way thanks to this inequality. So let me just well, I mean this because indeed because of this equation can be seen indeed as the gradient flow of some of the entropy. I mean rho t. I mean if there were no the divergence part, rho t would be. I mean this would be indeed the gradient flow of the entropy in the space in P2, but there is some control entering into play here. Okay, that's fine. And okay, very is this M here? Okay, sorry. Yeah. Okay, in this case, or reference measure, or yes. And okay, very briefly, since I think maybe my time is over, I sketch very briefly the proof, which is just the following. One has to look at the integral of the T Hopf-Kohl transform of psi, differentiate it twice, and one observed that doing so, the Carré-Duchamp operator comes into play, more precisely gamma at the first derivative and the iterated Carré-Duchamp at the second derivative. So one is able, using the CD condition, to estimate the second derivative by means of the first one. So using Grunwald, one gets this inequality, one integrates in time, and at the right-hand side, one gets another equivalent representation of the entropic cost. And that's all. Okay, I think I don't have time to discuss the stability, so I stop here and I thank you for your attention.
Are there any questions? Marks?
So here you show convergence of gradients. So it's more or less the same as convergence of Brunier's maps, right? Because the Brunier map is like the exponential of the gradient.
Mm-hmm.
And are there other estimators that you could study instead of just the gradients? For instance, I know in practice many people consider like the conditional expectation, like the barycentric projection. Or
okay, I see what. I mean, well,
it's equal to the gradient on the manifold.
Schrödinger potential is the barycentric map.
In Euclidean space, but not on the
in
manifold.
the Euclidean,
right?
yes, that's the point.
Is it true on the manifold? I think it's true only on the Euclidean space because it's like.
Yeah, indeed. I did not say it, but indeed.
Euclidean space is for losers, right?
If you in the Euclidean, exactly in the Euclidean case, when U is 0, so you have Brownian particles. Indeed, the two coincide, but otherwise the two are. I mean, there is no need. I mean, there's no reason why the two problems coincide. Indeed, they are different.
Or maybe for other costs that would not be the geodesic distance.
Okay, by the way.
I guess in your work.
Yes. Also because this has to deal with Schrödinger problem. So I mean, this means that at least so if one wants to extend this result, it's not like in UT that just replace C with a different cost. One has to replace here the particles with a different dynamic and look at the rate function, and which is usually a function defined on the path space, and see if this rate function can be then reduced to a static problem. So I mean the approaches are different, so I cannot answer to your question. Be
Thank
outside the Euclidean case.
Are there other questions? If not, let's thank Luca and all the speakers of this afternoon. We resume tomorrow at 9. Thank you.